The amazing Cassini spacecraft and its sibling lander Huygens have now concluded their scientific studies, bringing back years of data to be combed through by scientists, plotting their next journey to Saturn's space. Now it's time for other planets and other spacecraft to shine. Juno piercing the cloak of Jupiter, and her distant relative New Horizons at the edge of the solar system. After 20 years, the Cassini project finally comes to an end in dramatic style. But with one door closing, another opens. Now the enviable task of having to unravel the data Saturn has just laid bare begins. And they have literally just scratched the surface.
I think Cassini has left us with humankind's presence at another planet for 13 years, seeing things that we had never imagined seeing, and at the same time sharing that with the entire world and opening up vistas for the next sets of missions.
One of the issues facing scientists when looking at exploring the new frontier is leaving it in a better state than they found it. So eliminating the problems of space junk or the introduction of alien microbes is paramount in their decision-making.
But it also helps us satisfy a planetary protection requirement. We're protecting the tiny moon Enceladus as well as Titan. Both of those have global oceans underneath their icy crusts, and just in case there might be life in those oceans, we don't want Cassini to crash into one of those moons once we're out of fuel.
While the main focus of the Cassini mission was to delve into the mysteries of Saturn and its rings, the moons of Saturn proved most science-worthy. And Saturn has many moons. In fact, 62 with confirmed orbits. Several are only 50 kilometers in diameter, the largest being Titan, which is bigger than Mercury. The Huygens module that traveled aboard Cassini also became the first probe to land on a moon other than our own and transmit data back to Earth.
The temperature at the surface of Titan is about minus 180 degrees, so it's very cold. The landscapes of Titan look a lot like those we have on Earth. We have rivers, lakes, seas, almost oceans of methane. It rains methane or a mix of ethane and methane, so there are lots of meteorological phenomena or geophysical phenomena on Titan that makes you think of what happens on Earth. But the ingredients are quite different.
But it is Saturn's sixth largest moon that excited many scientists, as it is virtually covered by clean ice and ejected plumes of water into space.
My favorite moon is Enceladus, and the reason I'm partial to Enceladus is it's the moon that my team discovered a water vapor plume at. But not only is there liquid water underneath the surface, but there's organic material, there's a heat source. You know, when people get excited about the potential for life elsewhere in the solar system, there are four things that you need. You need a heat source, You need liquid water, you need organic material, and you need those three things to be stable over some period of time so that life could potentially form. At Enceladus, we've got three. We're not sure about the stability over time yet. And so based on the Cassini observations we made back in 2005, we've had lots and lots more flybys of Enceladus. We now understand it much better. We understand what organic material is there. I mean, one of the instruments, the ion neutral mass spectrometer, in a very close flyby through the plume, found some ammonia in the plume.
First of all, we see plumes. Then we start finding out from the gravity measurements and the imaging that there's an ocean and that it's global. And then there was some measurements by the cosmic dust analyzer that suggested there was hot water being circulated through the rock, the silicon dioxide nanoparticles. This is just the final step that shows that there's molecular hydrogen being produced by these same hydrothermal processes, and that molecular hydrogen has the chemical energy to support microbial systems in the interior ocean.
It's really the longevity of the Cassini mission that's allowed us to put together the pieces of the puzzle to really understand a moon like Enceladus. And even this late in the mission, we continue to look at our data to better understand this ocean world.
Collating data is one thing, but interpreting and providing vision for future missions is another. This is an area for which the Cassini project came up trumps, because it not only brought together three agencies, it provided the ground for future scientists to develop skills that will provide the basis for new projects.
The number of PhDs we've put through the system that are going to be the educators of the next generations. We've put out 3,000 plus peer-reviewed papers, hundreds of PhDs, thousands of peer-reviewed papers. The legacy, the scientific legacy is huge. The engineering legacy, of using every ounce of engineering capability to exploit a system, I think is again, we will be built upon. And I can't ignore the international cooperation. I mean, we had 19 nations contributing hardware to this mission. We've got over 26 nations now contributing scientifically.
The mighty Jupiter is the current target under the microscope with the Juno mission in full swing. The story of our solar system is linked to Jupiter, as it is believed that it was the first planet formed. So if we can understand how, we can begin to unravel the origins of our solar system, and thus how the Earth came about. Juno must work in a very harsh environment to tease out the answers from the gas giant.
When you go to a place as hazardous as Jupiter, we put a lot of time through the whole development process in trying to design a spacecraft that will operate in the high radiation fields, the magnetic environment, the spacecraft charging environment, everything that you deal with at Jupiter. And I have to say the spacecraft has been performing admirably.
Jupiter's radiation belts pose one of the biggest problems faced by Juno scientists. They exist within the enormous magnetic field that surrounds Jupiter, with its magnetosphere trapping and accelerating particles. It produces intense belts of radiation similar to Earth's Van Allen belts, but thousands of times stronger.
Juno just flew by Jupiter for the first time with all the science instruments on, and it was spectacular. The spacecraft performed flawlessly, the instruments all worked exactly as planned, and the data is amazing. We're looking deep into Jupiter, we're learning about the secrets that it's holding, but we're also getting a lot of surprises about the aurora, about the atmosphere, how it works. I mean, it's just incredible.
The flybys which followed showed that the massive amounts of energy swirling over Jupiter's polar regions were creating the giant planet's powerful auroras, but not in ways the researchers expected. What puzzled the researchers was the fact that despite the magnitude of these potentials at Jupiter, they are observed only sometimes, and are not the source of the most intense auroras as they are on Earth.
Juno had its camera, Juno Cam, on during the flyby. We got the first pictures of Jupiter's poles, the North and South Pole. They were amazing, a lot of surprises in them. It didn't look like we thought, doesn't look much like Saturn's pole.
Jupiter's poles are covered in these cyclones and anticyclone storms, some of them half the size of the Earth or bigger. And we're puzzled as to how they could be formed and stable in that configuration. And the North Pole doesn't look like the South Pole. And so we're questioning, the scientists are really questioning whether this is a dynamic system and are we seeing just one stage and over the next year we're going to watch it disappear? Or is this a stable configuration and that these storms are circulating around each other?
While the polar activity appears unique to our solar system, the engineers are looking below its shell for answers.
The new science results from Juno really are our first look at close up at how Jupiter works. And so the first time we're looking inside of Jupiter with into the interior, and what we're seeing is that it doesn't work at all like we had predicted. Almost every model that has the interior motion, how the magnetic field, the gravity field, how the deep atmosphere works, it's all different.
Like most scientific undertakings, they result in more questions being asked than answered.
So Juno's original objectives really were to understand how Jupiter formed, and that would help us understand how planets general form and how the whole solar system was made. What we're finding is that actually we didn't understand giant planet dynamics very well, the whole atmosphere or interior structure.
What we've seen so far is exciting, no question about that. But it's like a puzzle, and we're putting the pieces of the puzzle together, and it's exciting, but we don't have the whole picture yet.
And one of those puzzles is the so-called Great Red Spot. And while its presence in a turbulent gaseous planet is not unusual, the scale is. The red spot covers an area twice as large as Earth.
And we're going to go right over the Great Red Spot. And that's really going to be the first time that we get a close look at that and to see what it's like underneath the top surface layer. I mean, how deep are the roots to that? That's a 300-year-old storm. A lot of scientists believe that the roots must be very deep. Well, when we go over with our microwave radiometer, we're going to see, is it the same as the zones and belts, or is it very different? And nobody really knows.
But it's not just Jupiter's poles that hold the greatest interest for the Juno investigators. They are also intrigued by the weather pattern that is unique to this planet, yet familiar in other ways. Studying the atmospheric dynamics helps understand other planets' atmospheres.
So when we look at Jupiter, we see a lot of structure that looks very similar to the Earth. We can see storms, we see cyclones, we see anticyclones, and these sort of storms and weather systems that we see on Earth are very similar and they're happening on Jupiter. Fluid mechanics is hopefully the same everywhere in the universe, but Jupiter and Earth are very different. Jupiter's much bigger, it rotates a lot faster, they're made of different material, and Jupiter's much further away from the sun than the Earth is. The quasi-biennial oscillation, or the QBO, on Earth is an equatorial phenomenon in the stratosphere where the winds are changing direction approximately every 2 years. Depending on which phase the QBO is in, eastward or westward, the temperature signal corresponds to that. So it's warmer in the eastward phase and cooler in the westward phase. It's been shown that it can actually be a barrier to transport of aerosols across the equator and has been linked to the frequency and the formation of hurricanes in the Atlantic and the Pacific Ocean. The long-term scales on Earth's climate is something that we're very interested in, and how that applies to other planets' atmospheres is really why we're studying Earth and Jupiter. The quasi-quadrennial oscillation in Jupiter's stratosphere is a temperature signal that we see in the equator, where we see the temperature get warmer and cooler approximately every 4 Earth years. We used a general circulation model where we focused on simulating the effects of small-scale waves produced from convection in Jupiter's equatorial region to simulate the QQO. The waves propagate upwards from the clouds and force the winds in the stratosphere to change direction, going from eastward to westward approximately every 4 years. Our model was able to reproduce the behavior of the QQO, but was also able to reproduce temperatures from the observations, and both of those together give us a lot of confidence that our model is very accurate in what's driving the QQO. The outer planets serve as a laboratory for understanding atmospheric physics under very different conditions that are present on the Earth. Understanding how their atmospheres change and evolve and their climates can give us insight into any planetary atmosphere.
Juno has studied the planet with a suite of tools, revealing much that was previously hidden to the human eye.
We have an infrared instrument on Juno called JURAM, and it was designed and built and delivered by the Italian Space Agency. And this instrument makes thermal maps of Jupiter. So the images are showing you what's warm, hot, cold on Jupiter. And one of the things you can see right away is the center of some of these hurricane-like storms are cooler than the surrounding area. And sometimes you go over a warm spot. And we went over one that was very small that seems hotter than the surrounding area. And that's very similar to what the Galileo probe went into back in 1995.
The Juno mission is unique because it's the first time that we've ever gone in a polar orbit, which goes from pole to pole, over the North Pole, through periapsis, and under the South Pole. All the other missions we've done and all the observations we made from Earth were made from the equator. And you don't see the poles very well if you're sitting on the equator. Yes, this is the first time we get the first clear, unobstructed view of what the aurora looks like and what the polar phenomena looks like. And at the same time, we're flying through the magnetosphere right above the aurora, so we can sample in situ the charged particles that are precipitating down magnetic field lines, the guys that are exciting the emissions that we see.
Juno, like its sister Cassini, has a use-by date when the craft runs out of maneuvering fuel. This may occur during its 12th orbit at the end of its prime mission. However, NASA may choose to extend the mission if there are sufficient reserves. In that case, the deorbit would occur later, on the 34th orbit, as part of the planetary protection policy of NASA. Its pathfinding mission is leading the way for the one to come, the Europa Clipper, a mission in the design phase to look closely at Europa, the moon with a hidden ocean, and the possible location for life to evolve beyond Earth. The blue haze of Pluto's atmosphere, possibly a hydrocarbon smog, seen from 200,000 kilometers away by NASA's departing New Horizons spacecraft. A few years ago, the dwarf planet Pluto and its 5 known moons were just small dots in the outer reaches of our solar system.
One of the important things you should understand about Pluto is the real scale of it compared to the rest of the solar system. So we've come to the beach to really convey that scale and distance. So if I draw the sun as a 30-centimeter circle, then we have to walk about 35 steps this way in order to draw the Earth in the same type of scale. So we're walking the equivalent of 150 million kilometers, which we call 1 astronomical unit. Normally, Pluto orbits at about 40 astronomical units from the Sun, but it's actually quite an elliptical orbit, so it changes between about 30 and 50 astronomical units. But back to the Earth. So the Sun is over there at 30 centimeters, which means that the Earth should be about here, about 3 millimeters, something like this. If we were to draw Pluto in the same scale, it should be 0.3 millimeters, and it should be 1 kilometer down the beach. So I'm going to draw it. Now obviously I can't draw something that's 0.3 millimeters, so I have to draw Pluto a bit bigger. If this is Pluto, then its largest moon is Charon, which is about half its size. But Pluto has 4 other moons: Styx, Nix, Kerberos, and Hydra. So there's a lot going on around the Pluto system. It's not just a cold, dead, icy rock.
The spacecraft spent 16 months sending its data back to Earth, and scientists and non-scientists alike have been enthralled by what it has revealed.
If you go in closer to the surface, you can see this type of really diverse terrain. So you have a very bright region. These are flat plains. Not entirely sure how they formed yet, but there's a couple of leading theories. There's a huge range of mountains. There's all kinds of different aged surfaces. Some of them have lots of craters. Some of them have very few, which means they're younger. If you look in a lot of detail at some of the mountainous regions, you can see that actually they're a few kilometers high, but they're made of water ice. I mean, on Pluto, it's so cold that water ice is the hardest thing. It's more like rock. And so the stuff that forms the softer material is actually nitrogen ice.
Water ice on Earth is close to 0 degrees, but on Pluto, it's minus 230 degrees Celsius. And there's a glacier of nitrogen ice, called Sputnik Planitia, thought to be under 1 million years old. This is young by planetary standards, and no one knows yet how it formed or is renewed.
One of the really fascinating things is some of the surface coloration you can see in these images actually shows that there are these compounds called tholins, which are a combination of elements, but they're related to prebiotic molecules, so they're kind of relevant to prebiotic chemistry. And I think the fact that they have been able to form on planetary surfaces very far out in the solar system at very cold temperatures really has implications for a lot of places. I mean, if you can imagine for star systems outside our own, where the star may be dim and the planets are quite far away, it's interesting to know that there are molecules that could be involved in supplying biotic material to processes that may one day lead to life or be involved in life or something like that. They're actually forming way out in the solar system where no one really expected.
Pluto is unlike anything seen before. But the 6 gigabytes of New Horizons images and scientific measurements are giving scientists mysteries to unravel for years to come. In the meantime, asleep for the moment, the probe travels deeper into the unknown, soon to awaken at its next destination. Space is vast, yet collisions are commonplace. Gas and dust electrostatically flock together. Gravity takes over, coalescing grains into rocks, rocks into boulders, then asteroids colliding again and again, striking planets and each other. Stars collide, creating monsters of light and energy. Even galaxies collide over millions of years. Space is a rough place to be. That peaceful night sky cloaks a hidden danger. It might appear bejeweled, docile, and permanent, But if you look closely, you can see things happening, violent things. Stars engulfing planets and each other, protoplanets colliding, explosions rippling through gas clouds, triggering the birth of young stars, black holes devouring everything in their path. Closer to home, a more immediate danger is the debris from the creation of our solar system, spinning about in a heliocentric orbit just waiting to bang into something like Earth. Collision avoidance is the name of the game, and we now have the technology to do something about it.
Catalina Sky Survey and other survey programs are really sort of the start of the whole planetary protection ecosystem. It starts with discovery, goes on to follow-up and characterization, impact risk analysis, mitigation studies, but you can't follow up and you can't characterize and you can't calculate the impact risk of something you don't discover. In order to find a near-Earth asteroid, we take 4 images of a patch of sky separated by about 5 minutes.
And we take those 4 images and we blink them really fast, and it creates this little animation so we can see that the stars in the background are static, as they should be, and if there's anything that's moving, it'll pop out.
And our software compares those images and identifies things that are not moving, which are stars, and removes those, identifies things that are transient from frame to frame, and tries to link those up.
We've probably seen about 1 million asteroids in the last 7 years that the PanSTARRS has been operating. It's like picking a needle out of a haystack. We're looking for distinctive motion, and when we see distinctive motion in asteroids, we report them to the Minor Planet Center. The Minor Planet Center is the sort of world clearinghouse for near-Earth asteroids.
The Center for NEO Studies takes the observations from the Minor Planet Center and computes the high-precision orbits that we use to make predictions. CNEOS is also kind of an early warning system for newly discovered asteroids. We take the early data and we compute whether or not that asteroid could hit the Earth. If there's a chance, we'll send out an early warning and alert for follow-up observations so that we can get more data, and then we would know perhaps whether it can hit the Earth or not.
Asteroid impacts are a fact of life. The Earth has been impacted by asteroids continually through its history.
We saw in 2013 in Russia, a fairly small, by the standards of what we're finding, asteroid did hit the Earth. I feel a little bit like a guardian of the planet and doing my bit to try to protect people. It is a long-term process. It's going to take many, many years to find all of the dangerous asteroids.
The goal is to find near-Earth asteroids before they find us.
Having the right tools helps us look further away in greater detail. The Hubble Space Telescope was one such tool that was able to capture the first spectacular impact seen in our solar system. The Shoemaker-Levy 9 cometary fragments which struck Jupiter, leaving a surprising impression. Even more remarkable was the recent arrival of an interstellar object.
It was a special day when this object was first discovered. We have been waiting for the discovery of an interstellar object for decades, basically.
Well, when I first heard about this interstellar object, it was very exciting just from a scientific point of view that finally there's been an actual observation of such an object.
This object is simply a piece of another solar system that was expelled, and it has been traveling through interstellar space for hundreds of millions of years, billions of years, we don't know.
A number of our survey projects and other observatories immediately turned their telescopes to take observations of this object. From the observations we have so far, it looks like it's a very elongated object, maybe about a quarter mile in length.
We think this object, 2017 U1, is very long, perhaps 400 meters or so long, and very narrow, skinny, perhaps maybe 40 meters or so in the other dimensions. That's a very unusual shape. We don't see that in our solar system. None of the asteroids in our solar system look like that. So it's very puzzling how it could have obtained this shape.
We also see that it's very reddish in color, which indicates that it's been possibly in space a long time and irradiated by not only the light from our sun, but other suns as well.
Well, there's still quite a bit to learn about this interstellar object and limited time because it's on its way out of the solar system.
It's fading very fast. It's a relatively small object, so it's very dim. But we are continuing to try to use NASA assets like the Hubble Space Telescope and Spitzer to take observations to determine more about its size and composition.
NASA's Planetary Defense Coordination Office has a near-Earth object observations program which funds efforts that survey the skies to look for near-Earth asteroids and to calculate their orbits and their trajectories and to determine if any of them might pose a hazard to Earth. And as part of doing that, some amazing discoveries can happen, and the discovery of this interstellar object was one of them.
As our observational capabilities improve, Pan-STARRS has been getting better, other surveys have been getting better. There are new generation surveys that will come online. We will be detecting more of these in the future.
New observatories are being constructed. To be launched in the coming year, the James Webb Telescope will orbit at Earth's L2 Lagrange point 1.5 million miles from Earth, away from the Sun. Its low-temperature sensors will be shielded from the Sun, Earth and Moon. There are also 3 new ground-based observatories underway. A multinational project being built in Hawaii, the 30-meter telescope, or TMT, will use 492 hexagonal elements, each about 1.44 meters, to construct the single primary mirror of 30 meters diameter. The secondary mirror will be 3.1 meters in diameter. The largest of all will be Europe's Extremely Large Telescope, or ELT. The primary mirror consists of 798 segments, each 1.4 meters wide, but only 50 millimeters thick, with a light collecting area of 978 square meters. The optical design calls for an immense secondary mirror, 4 meters in diameter, bigger than the primary mirrors of any of ESO's telescopes at La Silla. Then there is the giant Magellan telescope, currently under construction in the Chilean Andes, which will be ready by 2022. It consists of 7 8.4 meter diameter mirrors, making a total effective aperture of 24.5 meters. Housed in a rotating 22-story high building, it will produce images 10 times sharper than Hubble, with a total collection area of 368 square meters.
This is a project that we began in 2003. It was a small group of U.S. institutions and has now grown to an international project that includes Australia, Korea, Chile, and most recently, Brazil. The next steps as we launch construction of this telescope are to build the mount, the steel mount that will hold the mirrors for the telescope, to build the enclosure, which is a 22-story building that has to rotate to allow you to move to different parts of the sky as you're looking out with the telescope.
It's a new epoch in the field of astronomy. It's a new epoch for cosmology, astrophysics, and the history of the universe. And so we'll be able to see things further and fainter than anyone has ever seen before.
It just takes us to that next level of technical capability, and these technical leaps are what enable new discoveries.
The first 4 giant mirrors for Magellan have been manufactured. Number 5 is underway, as is construction at the site in the Chilean Andes.
GMT is really an exciting thing because we know that over the last 400 years that telescopes have gotten bigger, and that has allowed us to see things with better detail and to see fainter things and to figure out what the history of the universe has been. Our technology for doing this is getting better and better. We're able to build big mirrors, and we know how to do this. We know how to build GMT. We know how to build its individual mirrors and put them together. We know that when you build a telescope view, and the GMT will have a view that is 10 times sharper than the Hubble Space Telescope. And when you build a telescope that collects more light, and the GMT will collect 100 times as much light as the Hubble Space Telescope does, that you are going to be able to do things that we can imagine and set out as our goals, to look at the history of the universe, how things have changed, find out more about the dark energy and the dark matter. Those are things that we know you can do. But I think the really exciting things will be things that we haven't yet thought of, that the new questions that will come. The other part that's really interesting about a big telescope on the ground is that you can change it. That is, you can change the instrument. So I think that even when we build the telescope, that won't be its final form. Those instruments will eventually be replaced by better ones that use the technology that's developed over the period from now to then. We know that the universe has changed from a very homogeneous kind of goo at the time of the Big Bang into a highly differentiated world where there are planets, stars, galaxies, clusters of galaxies. The universe has gotten kind of interesting and complicated through the action of gravity over time. We'd like to see how that works. And by looking at what happened long ago, which means looking at very distant, very faint galaxies, and looking in detail, which means having the resolution to kind of really see what's going on.
No doubt revealing cosmic collisions far back in time and space. Not as close as the asteroid field, but still in our neighborhood, are other phenomena colliding in space. Out beyond the edge of our galaxy, the Milky Way is a cloud of hydrogen gas called Smith's Cloud, after its 1963 discoverer, Gale Smith. It is traveling at 312 kilometers per second and is about to collide into the Perseus arm of our galaxy. Well, in 27 million years or so. It was believed to have been ejected from the Milky Way some 70 million years ago. Why is still not known, but when it collides with the galactic arm, it will trigger a brilliant burst of star formation with enough gas to produce over 2 million stars. Another major event to occur soon is in the heart of our galaxy, where a supermassive black hole resides. This black hole's mass is a hefty 4 million times that of the Sun. ESO telescopes have been tracking the motion of stars around the giant black hole for 20 years. Although huge, it is currently supplied with little material and is not shining brightly. But that is about to change. Recently, they have discovered a cloud of gas traveling towards the gravity sinkhole on a collision course.
The cloud consists mainly of hydrogen gas which we see anyhow in the galactic center all over the place. This particular cloud weighs more or less 3 times the mass of Earth, so it's a rather small and tiny blob only, but it glows very brightly in the light of the stars which are surrounding the cloud.
We really don't know where the cloud came from, but we do know that most of the material which is currently flowing into the galactic center black hole comes from stellar winds, material which is ejected by nearby stars. And could be that this particular cloud also was coming from a star ejecting material, but happened to produce a very compact and directed right at the black hole. Well, the next few years will be really fantastic and exciting because we are probing new territory. Here this cloud comes in, gets disrupted, but now it will begin to interact with the hot gas right around the black hole. We have never seen this before. We expect it gets hotter. It may even start emitting X-rays, very hot radiation, and then it gets disrupted, and then in the end we expect it to fall into the black hole once it's sort of going through all of this churning.
As the astronomers watched, the cloud has been picking up pace as it gets closer to the giant black hole. Its speed has doubled in the last 7 years, and it is now speeding towards the black hole at more than 8 million kilometers an hour. The astronomers have already seen the cloud's outer layers becoming more and more disrupted over the last few years as it approaches the black hole.
The black hole, imagine it sitting here, has a tremendous gravitational force, and the cloud, as it comes in, it will be elongated and stretched. It will become essentially like spaghetti. It will be elongated and falling into the black hole.
Observations of other massive black holes at the center of galaxies have revealed many varied phenomena. One galaxy's supermassive black hole is emitting a powerful outflow of material and, to the surprise of astronomers, is forming stars. Results from ESO's Very Large Telescope are the first confirmed observations of stars forming in this kind of extreme environment. The discovery has many consequences for understanding galaxy properties and evolution. Black holes at the centers of galaxies still hold many secrets. Galaxies are the building blocks of the universe. The giant galaxies we see today, even our own, were built up from many smaller galaxies, and construction isn't over. Today, full-grown galaxies approach and interact with each other. They may collide and eventually merge, growing larger and more influential. As the galaxies approach each other, the tug of gravity creates tides that distort their shapes. Stars and gas stream into new orbits. Sometimes they're completely ejected, trailing into the depths of intergalactic space. Clouds of gas are compressed in the chaos and ignite with intense rounds of new star formation. Computer simulations have been conducted and, compared to actual images of galactic collisions, an uncanny resemblance. Because stars create most of the chemical elements, each galaxy has a particular chemical makeup. This makes identifying groups of stars from different galaxies easier. This infrared image of our sky shows our point of view of the Milky Way, 500 million stars. Most are in our galaxy, some belong to companion galaxies that orbit our Milky Way, and some are in between. Astronomers have discovered that some groups of stars belong to a different galaxy called the Sagittarius Dwarf Elliptical, and the Milky Way is cannibalizing it. As the dwarf galaxy passes through the Milky Way's disk, Gravitational tides stretch the dwarf stars into long streams that wrap around the galaxy's orbit. For the dwarf, it's a fatal attraction. For the Milky Way, just another one of several similar events in its history. But something much bigger is headed our way. M31, the Andromeda Galaxy. This is the Milky Way's biggest neighbor, of roughly the same size, mass and type, and it is speeding towards us. Astronomers say the crash will begin in about 2 billion years. Supercomputer simulation shows how the event may unfold over billions of years. The first path distorts the 2 great spirals. Stars are tossed into the intergalactic night like sparks thrown from a campfire, and our sun, complete with planets in tow, could be similarly ejected. Gravity will eventually merge Andromeda and the Milky Way into a bigger single entity. With a new generation of telescopes looking skyward, we are sure to discover more dangers lurking in the heavens, though fortunately for us, they are millions or billions of years in time and distance away. The Soviet-era Luna 3 was the first spacecraft to use gravity to change course to photograph the dark side of the Moon. The NASA Mariner 10 mission used the technique to swing by Venus to target Mercury. The gravity assist or Sling Shot maneuver has become a standard for navigating the solar system, with our probes reaching further, faster and more accurately than ever before. The Voyager mission started by chance over 40 years ago, when Michael Minovich, a mathematics PhD student, decided to tackle celestial mechanics' holy grail. It was known as the three-body problem, as it looked at the Sun, a planet, and a third object traveling in space, and how gravity from the 2 objects affected the trajectory of the third. Minovich was eager to take advantage of IBM's latest computer, the 7090. This computer was a second-generation transistorized version of the IBM 709, a vacuum tube mainframe which had a processing speed of around 100 kiloflops per second, unthinkably slow by today's standards. The laws of physics and the conservation of momentum demand that the probe approaching the gravitational influence of the planet and accelerating will then decelerate upon leaving that gravitational field with a net speed increase of 0. However, the probe's speed and direction will change in reference to the Sun. His solution has become known as gravity assist or Sling Shot. While undertaking an internship at NASA's JPL, he convinced them to test his model using their data. The results confirmed his predictions that if it flew close enough to a planet, a spacecraft could utilize that planet's motion to accelerate itself away from the Sun. When Caltech graduate Gary Flandreau was tasked to see if gravity assist could aid deep space missions to the outer planets, he discovered there was to be an alliance of Jupiter, Saturn, Uranus and Neptune, an event that occurred only once every 176 years, an opportunity not to be missed. So it was decided to launch a mission in 1977. 2 spacecraft would be launched, which would slingshot past all 4 of them, a grand tour of the solar system's outer planets in a 12-year time frame. This was to become known as the Voyager missions, and the rest is history.
Ultimately, we're able to put together a picture of where we are in the galaxy and how that environment then influences our environment right here at home. In particular, the radiation environment, which has implications for all sorts of things, including human exploration of space.
Today, those 2 spacecraft have continued on beyond the influence of our Sun into interstellar space, the farthest traveled by a man-made object. This field of influence formed the basis for all future missions, allowing man to set his sights on getting into deep space economically. The Rosetta mission had different challenges: to catch up with and orbit a comet, 67P Churyumov-Gerasimenko. It had a large elliptical orbit around the Sun, stretching from the orbit of Jupiter to within the orbit of Mars. Launched in 2004, a year later the probe passed by Earth for the first gravity assist that flung it towards the orbit of Mars. Two years later, Rosetta grazed Mars, building up momentum, then swung by Earth for a second time, launching it deeper into space. The following year, Rosetta passed by asteroid Steins before swinging back for a third gravity assist from Earth. And in 2010, Rosetta passed by asteroid Lutetia. Going into hibernation, Rosetta continued its parabolic trajectory towards its final destination. 4 years later, Rosetta emerged from its cold sleep as it crossed paths with the comet, a circuitous flight indeed. The spacecraft then embarked on a series of maneuvers that took it on 2 successive triangular paths. Its trajectory was fine-tuned with thruster burns until it closed in to within about 30 kilometers of the comet, where the spacecraft entered actual orbit around it. Rosetta remained with the comet, delivering it cargo, then conducting science observations as it swung about the Sun, then concluded with a gentle impact on the comet's surface in 2015.
We're going to refine our ideas of what the comet is, where the comet came from, and encapsulate that within our ideas of how the solar system formed. And the complexity of the data set that we have also allows us to be more complex in our ideas and our theories. And that is the beauty of Rosetta, and we're starting to see that happening now, that we're really able to hone down our ideas of how the comet formed, how that fits in the evolution of the solar system, and that's going to continue.
The Ulysses spacecraft had to leave the ecliptic plane of the solar system to study the polar regions of the Sun. Accordingly, it needed to change its orbital inclination. This required a large change in heliocentric velocity, so a gravity assist maneuver around Jupiter was chosen. The giant planet's gravity bent the spacecraft's flight path southward, putting it into an orbit over and under the Sun's north and south poles. The ion-powered Dawn spacecraft took maneuvering a step further.
Dawn's the only spacecraft ever in more than 58 years of space exploration to orbit 2 extraterrestrial destinations, the last uncharted worlds in the inner solar system. And it not only allows us to get to these distant bodies, but once we're in orbit, we can maneuver extensively in order to get the best possible science that we can from the mission.
NASA's latest mission is underway. OSIRIS-REx is the agency's first attempt at intercepting and touching down on an asteroid. No ordinary asteroid either. Bennu is its name. Orbiting the Sun very closely to Earth's orbit, it has been deemed a possible impact threat in the coming centuries. NASA intends to take a sample of the asteroid and return it to Earth for further study, and possibly help form plans to redirect Bennu. To match the orbit, OSIRIS-REx made a very close swing by the Earth a year after launch. It passed by the South Pole to change its orbital inclination several degrees to match that of Bennu. Once matching orbits, OSIRIS-REx must perform a series of braking maneuvers to match velocity and enter an orbit around the asteroid. After mapping and studying the body, OSIRIS-REx will drop down to the surface and collect a sample of material. With some clever robotics, the sample return capsule will be delivered back to Earth.
Well, the thing that is so intriguing to me about asteroids is that they really are time capsules. They actually are samples of what the solar system was like billions of years ago. Asteroids are small bodies that never got made into something big like a planet. So anything that got made into a planet got melted down, got changed. There were lots of things that went on. Asteroids are pristine. Nothing really altered them for billions of years. So when you go out and you take a sample of an asteroid, you have in your hands a real sample of what the solar system was like billions of years ago. What were the conditions? What was the chemistry like? What can you learn about the formation of our own planet and ourselves by looking at what the solar system was like billions of years ago? And this sample is incredibly scientifically important. I think that people will be studying it for generations to come.
The Juno space vehicle was launched in August 2011. In 2012, at perihelion, the craft performed some maneuvers out beyond Mars orbit and arched back towards Earth for a kick in speed and direction. In October 2013, it flew by Earth a mere 500 kilometers from the surface. This Sling Shot sent it on a 3-year journey directly towards an interception with Jupiter.
Jupiter orbit insertion is probably one of the most important things in the entire mission, and it's because that changes us from being in orbit around the Sun to being captured in orbit around Jupiter. And if you're not in orbit around Jupiter, you can't do the science we want to do. And what we're learning now is even in other solar systems, they don't always all have a monster like Jupiter. And many people think, boy, you almost need a Jupiter to have an Earth maybe. Jupiter played a big, important role. But its environment, everything about it is extreme. It's a planet on steroids, right? It is the most extreme in every way it can be. So it has the strongest magnetic field, the strongest gravity field. It has the most harsh radiation. It's spinning super fast. I mean, everything about it is this extreme environment.
The Juno mission is unique because it's the first time that we've ever gone in a polar orbit, which goes from pole to pole, over the North Pole, through periapsis, and under the South Pole. All the other missions we've done and all the observations we made from Earth were made from the equator. And you don't see the poles very well if you're sitting on the equator. Yes, this is the first time we get the first clear, unobstructed view of what the aurora looks like and what the polar phenomena looks like. And at the same time, we're flying through the magnetosphere right above the aurora, so we can sample in situ the charged particles that are precipitating down magnetic field lines, the guys that are exciting the emissions that we see. This is the first time we've ever been able to do that.
The 6.7-year, 5 billion kilometer transit journey of the Cassini probe was slightly longer than the direct Hohmann transfer. The mass of the Cassini spacecraft was such that even with the Titan IV launch vehicle, Cassini needed added help to reach Saturn. So, to gain momentum, the Cassini mission included several gravitational slingshot maneuvers. 2 flyby passes of Venus, 1 of the Earth, and then 1 from the mighty planet Jupiter. The Cassini orbiter then spent several years orbiting and maneuvering around the planet and its moons, finally diving through the inner rings of the planet.
When we go into the proximal orbits between the rings and the planet, we've never been there before, and we'll be a little bit more concerned. Here, we've actually been closer to these rings, the Janus Epimetheus ring and the F ring, when we went into orbit around Saturn. So this is not unexplored territory at this point. The nice thing about this, though, is that we've got a much better viewing angle of the rings because of the sun this time around.
And eventually into its atmosphere. The New Horizons spacecraft had further to go than Cassini, but being far less massive a probe, it was able to be launched directly towards Jupiter. The spacecraft was launched in 2006 and made its way to Jupiter. Its closest approach happened only a year after its departure, at a distance of 2.3 million kilometers. The flyby provided a gravity assist that increased the probe's speed. It also allowed for a general test of New Horizons' scientific capabilities, returning data about the planet's atmosphere, moons, and magnetosphere. Most of the post-Jupiter voyage was spent in hibernation mode to preserve onboard systems. In 2014, New Horizons was brought back online for the Pluto encounter. It flew 12,500 kilometers above the surface of Pluto, making it the first spacecraft to explore the dwarf planet, and then on into the Kuiper Belt towards its next target, a Kuiper Belt object most likely composed of frozen volatiles or ice, such as methane, ammonia, and water. A future probe to return to Jupiter's moons is destined for another multi-year journey. JUICE, to be launched in 2022, will embark upon a 7-year odyssey, taking the spacecraft via an Earth swing-by, then to Venus, back to Earth with a slingshot to Mars, then back to Earth for a final kick, direct to Jupiter. Heading outward bound is one thing, but launching payloads inward towards the Sun is another set of problems. For example, the Bepi-Colombo mission to Mercury, launching this year, will require 9 gravity assist maneuvers. After launch, a 2-year journey using ion propulsion will bring it back to Earth for a kick towards Venus. followed a year later by another flyby of Venus, sending it closer towards the orbit of Mercury. In the following 4 years, the spacecraft will pass by Mercury, tightening its heliocentric orbit until it can match Mercury's speed, and with the aid of chemical rocket motors, insert itself into that planet's orbit in 2025.
So studying Mercury is crucial to better understand the formation of our solar system, how Earth is formed and evolved, and where we are coming from. So Mercury is in a way a missing piece in the big puzzle of the formation of the solar system, and a crucial end member because it's close to the Sun, and if you want to get this full picture, you have to look at the planet close to the Sun, as we also did in past missions that we were looking at the comets or planets further out.
Our aim, main target is the environment around the Mercury, especially the interaction between the solar wind and the Mercury magnetosphere.
Mercury is 3 times closer to the Sun, and therefore the radiation or the heat which we are getting from Mercury is 10 times higher. So everything which we had to develop had to withstand the higher temperatures, but also the higher radiation doses which we got from the solar wind. And for that we need special insulation of our spacecraft, special materials to be developed for the antenna, for the solar panels. And that was a very big challenge for the mission in itself.
There are 2 more missions in the next year or 2 that will travel further inward than Mercury: ESA's Solar Orbiter and NASA's Parker Solar Probe. Planned for a 2018-19 launch, ESA's Solar Orbiter will take several gravity assists from Earth and Venus to enter an elliptical orbit resonant with Venus, so that subsequent gravity assists will raise the orbital inclination, resulting in an operational orbit of 25 degrees inclined to the ecliptic plane and increasing to 34 degrees, making direct viewing of the Sun's polar regions possible. During the nominal 7-year mission, the main scientific activity will take place during the near-Sun encounter and high-latitude parts of each orbit, with different science goals planned for each orbit. Together with NASA's Parker Solar Probe mission, it's hoped it will revolutionize our understanding of the Sun, where changing conditions can percolate out into the solar system, affecting Earth and other worlds. Launch window is late 2018. It will use Venus gravity assists during 7 flybys over nearly 7 years to gradually bring its orbit closer to the Sun. At closest approach, the Parker Solar Probe will travel around the Sun at approximately 700,000 kilometers an hour. Some 10 times closer than Mercury, the front of Parker Solar Probe's solar shield faces temperatures approaching 1,377 degrees Celsius. It will travel through the Sun's atmosphere, closer to the surface than any spacecraft before it, facing brutal heat and radiation conditions, and ultimately providing humanity with the closest ever observations of a star. Flying into the outermost part of the Sun's atmosphere, known as the corona, for the first time, Parker's Solar Probe will employ a combination of in-situ measurements and imaging to revolutionize our understanding of the corona, expand our knowledge of the origin and evolution of the solar wind, and explore what accelerates the solar wind as well as solar energetic particles. It will also make critical contributions to our ability to forecast changes in our space environment that affect life and technology on Earth. The interface between Earth and space is the ionosphere, a region of rarefied gas and charged particles. It is very important for radio communications, radar, satellite signals, and global positioning. Yet we know so little about it, especially when it disrupts all these signals in a regular fashion. Too high for planes or balloons, it's up to satellites to study this rarefied region. We have become so reliant on radio signals bouncing off the upper atmosphere and beaming down from satellites that the ionosphere has become a critical part of our technology. From aircraft communications and radar to managing navigation of the world's shipping lanes and global positioning for fishing trawlers to locate their catch. GPS for the military, on the ground and in the air. Yet we know very little about this region of Earth's atmosphere. Critically, there are times when global positioning signals become unreliable. The satellite and radio signals twinkle in much the same way as bright stars appear to do at optical wavelengths. Irregularities in the ionosphere, referred to as ionospheric depletions or bubbles, span the hemispheres at the equator and are a major element of the low-latitude geospace region.
It's very important for us to understand the ionized portion of the atmosphere, the ionosphere, as well as the upper atmosphere, because that's where satellites are, low Earth orbiting satellites are orbiting in that region. Astronauts are exploring that region, as well as the communication and navigation signals travel through that region. And so when you have disruptions in the ionosphere and variability in the ionosphere, that can affect our navigation and communication systems.
The ionosphere lies some 40 to 600 miles above Earth's surface. The upper atmosphere and ionosphere change constantly in response to forces from above and below, including explosions on the Sun, intense upper atmosphere winds, and dynamic electric field changes. These irregularities form huge horseshoe arcs between hemispheres, with their apices centered on the magnetic equator. To learn more, NASA conducted a mission called CINDY, the Coupled Ion Neutral Dynamics Investigation. CINDY was designed to measure ionization of the upper atmosphere, including the behavior of the irregularities responsible for the GPS twinkling, which turned out to be quite surprising. The ionosphere becomes unstable shortly after the sun sets. As darkness falls, ionized atoms and molecules begin to recombine into a neutral state. During this transition period after sunset, irregularities are quite strong. As the night wears on, however, these irregularities were thought to fade and eventually vanish around midnight. Cindy found many irregularities around sunset, but they did not vanish around midnight. On the contrary, there was another peak in irregularities during the middle of the night. This second peak has appeared most pronounced from June through August. Scientists aren't sure yet why this second peak occurs or why it varies by season. The Cindy mission ended with the re-entry of the spacecraft into Earth's atmosphere. Researchers still had much to learn about the ionosphere and how it can affect GPS and other satellite systems. To understand the tug-of-war between Earth's atmosphere and the space environment, NASA created the ICON satellite.
So with the ICON mission, we're looking at the very upper levels of the Earth's atmosphere and the charged plasma environment that surrounds the Earth that we usually consider as the inner edge of space. So that region is called the ionosphere, and that's what gave us the name for the Ionospheric Connection Explorer. But really a lot of what is happening there is being driven by the winds and the composition of the Earth's atmosphere.
So these altitudes, the thermospheric altitudes that the ICON mission is investigating are typically too low for satellites to fly in and too high for weather balloons to get to, for example. So we need to use remote sensing techniques to get the information at the right altitudes. And the atmosphere actually helps us do it because there is something called an air glow. The atmosphere naturally just glows at those altitudes, more during the day and less during the night, but it's always there. This air glow is always there. And by just looking at the color of this air glow, we can find out about the wind and the temperature, actually. So it's the atmosphere, in a way, is helping us to understand how it is behaving by sending out this air glow. And if we build the right instruments to look at particular aspects of the color of the air glow, we can get the information that we want.
So what ICON is trying to do is observe these two systems at the same time from one satellite. So it does that with 4 instruments, and broadly speaking, 3 of those are kind of camera instruments that look out at the Earth off on the horizon. One of them measures the temperature and wind of that atmosphere. One of them measures the composition of the atmosphere. One of them is getting the plasma environment, this charged particle environment. And then there's a 4th instrument that measures the charged particles and their motion and things at the location of the spacecraft.
High-altitude wind shear is thought to be one of the factors for GPS twinkle.
It's just the movement of the atmosphere, same thing as we experience as wind down here, except for the winds are generally much faster up there, and there's very little atmosphere, so the pressure is very, very low. So those are the 2 major differences between what we think of when we say the word wind here and what we experience up there, or what the instrument sees up there.
ICON was placed aboard a Pegasus rocket and flown into the stratosphere under the belly of an orbital ATK aircraft. Once it is at the right altitude and heading, the rocket drops away, then ignites its main engine, carrying the spacecraft into orbit. Once in orbit, the spacecraft is commanded by scientists at Mission Operations Center at the Space Sciences Laboratory at UC Berkeley. ICON then began its study of the frontier of space, the dynamic zone where terrestrial weather from below meets space weather from above. In this region, the tenuous gases are anything but quiet, as a mix of neutral and charged particles travels through in giant winds. These winds can change on a wide variety of timescales, due to Earth's seasons, the day's heating and cooling, and incoming bursts of radiation from the sun. To understand what drives the variability in the ionosphere is very complicated, a system that is driven by both terrestrial and space weather. A second satellite mission was needed, another suite of instruments in a higher orbit named GOLD. A first for NASA, GOLD was piggybacked on a commercial satellite.
The GOLD mission stands for Global Observations of Limb and Disk, and it's a very important mission for us to understand the upper atmosphere of the Earth, the thermosphere and ionosphere of the Earth. It is our first hosted science payload that NASA's flying on a commercial spacecraft. And so that is a new innovative way for us to do science that maximizes our private sector partnership as well.
GOLD will be sitting 22,000 miles above Earth, which means that it can see a whole half of the Earth, all of the Western Hemisphere. And it will be hovering over one particular point on Earth, watching the dynamics of the atmosphere play out below.
From geosynchronous orbit, GOLD can scan half the planet at a time.
I am excited about this mission because GOLD will be getting information about the upper atmosphere much faster than ever before, and we'll be able to look at effects that are more like the weather that we experience down here on Earth.
The two influences on the ionosphere are space weather and weather below, closer to the ground. Space weather is the realm of the sun, coronal mass ejections affecting our magnetic field and showering us with energetic particles. The sun's energy starts in its core, a giant fusion engine where hydrogen atoms are turned into helium atoms. The energy produced there moves up through the convection zone to the sun's surface, the photosphere. Moving magnetic fields contribute extra energy along the way, bursting from the surface, emitting light and heat that is channeled by the sun's magnetic field, generating the turbulent surface, including prominences, flares, and coronal mass ejections that spread out into the solar system.
Space weather is the field that studies how what's going on the sun affects us here on the Earth in our near space environment and on the space environment on other planets.
These powerful bursts of energy travel outward toward the planets. This space weather, consisting of light and thermal radiation, includes high-speed solar wind and energetic particles which collide into planets orbiting the sun. Earth has some defense, its magnetic field that deflects and absorbs much of the energy, distorting the magnetic field. Some energy is captured and follows the magnetic lines to the poles, generating auroras.
NASA hopes to achieve with the GOLD and ICON missions a better understanding of the near-Earth space that's so important for our global infrastructure.
To help predict space weather, many Sentinel satellites watch the Sun closely. IRIS is one of them. It watches our star in ultraviolet wavelengths and is able to give us warnings of extreme space weather events approaching Earth. This space weather has a direct influence on our ionosphere. Another tool to watch both the solar weather and Earth's weather together is about to go into operation, replacing its aging predecessor. GOES-R is a next-generation weather satellite with the latest in technology. It will be 5 times faster, advanced resolution cameras giving greater coverage for hurricane tracking, real-time mapping of lightning, and improved solar flare monitoring. Almost by accident, the Fermi X-ray telescope in Earth's orbit discovered another source of gamma-ray particles coming from Earth. Under just the right conditions, lightning storms fire off some of the highest energy light naturally found on Earth, terrestrial gamma-ray flashes, or TGFs. Rising and falling snow and ice particles repeatedly collide, filling the cloud with electrical charge. Once the electric field is strong enough, a current flows and a lightning flash occurs. The flash produces an abrupt reconfiguration of the electric field. In some cases, a surge of electrons rushes towards the upper part of the storm at speeds nearly as fast as light. When deflected by air molecules, these accelerated electrons give off gamma rays, producing a TGF. Data from NASA's Fermi Gamma Ray Space Telescope suggest more than 1,000 TGFs occur each day all over the globe. Tropical storms far from land tend to generate less frequent lightning. Nevertheless, observations show they are surprisingly prolific producers of TGFs. Tropical storm Manuel made landfall just shy of hurricane strength. As it rapidly weakened, it produced 2 TGFs within 24 hours. More typically, TGFs are associated with the strengthening phase of a storm. As Typhoon Bolavin rapidly developed in 2012, thunderstorms nearly 500 miles from its center launched a TGF with 4 distinct pulses. So far, the record holder for TGS is the rapidly strengthening tropical wave that later gave birth to Hurricane Julio. It produced 4 TGFs within 100 minutes. A 5th followed the next day, with nothing further. For stronger storms like hurricanes and typhoons, TGFs are more common in the outer rain bands, which host the highest lightning flash rates in these storms. The findings provide new insights into the relationship between storm intensity, lightning frequency, and TGFs. This adds another important piece to the puzzle of our understanding of TGFs and how they are created in thunderstorms, the most powerful natural particle accelerators on planet Earth.
ultimately, the science that we learn from Golden Icon will help us be able to predict the near-Earth environment that affects our communication and navigation signals and capability, but also how space weather affects the upper atmosphere, which can translate to effects on the ground in terms of our power systems and our navigation systems down below.
The march of technology must go on. ESA and the European Union can see the future of global positioning, and it is a growing market, with more and more technology requiring their services. The Galileo program is nearing completion with a total of 26 satellites orbiting at 22,000 kilometers. The penultimate launch of 4 Galileo satellites aboard an Ariane 5 will occur soon. As with all other Galileo satellites, these newest additions will fly in a medium Earth orbit. The last launch of 4 satellites will occur in the near future. Although the constellation is not yet complete, it has been in operation for almost a year since the European Commission announced initial services on the 15th of December 2016.
The completion of the constellation will take place in the summer of 2018, where we launched the last Ariane 5 with 4 satellites, which will bring the total up to 26 satellites. So we have at that moment 2 satellites in reserve, and we will then, after that, start putting some extra reserves in space in order to be prepared just in case.
These services were the first step towards full operational capability and a first opportunity for the Galileo system to prove its worth. Independent measurements have since shown that in terms of performance, Galileo is the best operating positioning system in the world.
On the 15th of December 2016, the Commission announced initial services. This was an important moment because this was the first time that we formally announced that there was a certain service available with a certain quality for a certain time of the day. Since then, we have been building out the constellation, and it has been improving every day. We now have independent measurements of the performance of the Galileo system, and it is actually, to be honest, and we are very proud of it, the best in class. We are having a better performance than our 3 competitors from the US, which is the well-known GPS system, the Russian GLONASS system, and the Chinese Baidu system. So, of course, in ESA we are excessively proud of this, and it is now important that we keep building on this performance and hopefully keep at the forefront of the developments.
But the work on Galileo is far from done. The European Commission and ESA are already working on the next generation of Galileo satellites and infrastructure. They aim to continuously improve the system and explore the boundaries of technological possibilities while trying to meet market demand with potential new applications or services.
The system will undergo continuous improvements. Obviously, the market is asking for that. The technology is ready for it. Every couple of years, there are new possibilities. And the combination between what the technology can offer and what the market is demanding leads then to decisions on how to improve the system so that we can provide further and more services. A number of areas, for example, which are coming is the so-called Internet of Things, which will require positioning in sensors. And these sensors have very little power and very little battery capacity, so we need special signals for that, probably. And in addition, another area which is of interest is autonomous driving, where satellite navigation is going to be a very important component, but where it needs to be integrated with all sorts of other sensors in cars in order to make sure that autonomous driving becomes a reality.
With more launches to complete the constellation and set up redundancies, Galileo's performance and availability worldwide will continue to improve gradually, keeping Galileo at the cutting edge of satellite positioning technology. Today, the only publicly owned satellite system has also proven to be the best. For over 50 years, we have bombarded Mars with our probes and landers, spying from orbit to map the terrain, finding her strengths and weaknesses. On the surface, probing for her resources and learning of her defenses. The next generation of robots are readying to establish the beachhead. The time is approaching for the full-scale invasion of the planet, when humans walk on Mars and claim it for their own. The conquest of this enigmatic planet so far away has been both challenging and rewarding. ESA has delivered the latest conspirator, the ExoMars Trace Gas Orbiter, to search out the source of methane in the atmosphere. Its landing craft, the Schiaparelli lander, failed and crashed, yet another victim of Mars's defenses. The ExoMars orbiter, now captured by Mars's gravity, has begun the challenging process of adjusting to a circular orbit without fuel. This involved using the shifting Martian atmosphere to gradually slow the satellite in a process known as aerobraking.
With ExoMars, ESA is going to use for the first time a method called aerobraking for a spacecraft in orbit around Mars to decrease the orbit by letting it fly through the atmosphere and using the atmospheric density to slow it down instead of using fuel for the engines.
We have to take a lot of margin to be sure that even if we go through a moment where the atmosphere is more dense at the altitude where we are flying, we are still safe with the spacecraft.
That aerobraking process took more than a year to complete. It was complicated by the changing nature of the Martian atmosphere.
The Trace Gas Orbiter is really looking at active processes ongoing on Mars today, and life, present life, is one of the possible explanations. So it will be really a Sherlock Holmes work to try to put together a case for whether it's geological or biological activity that is responsible for the methane.
Meanwhile, plans are well advanced for the ExoMars 2020 mission, with the final design of the rover nearing completion. And scientists have shortlisted two possible landing sites to put it to use: Oxia Planum and Morth Vallis. Both are shortlisted because they have had an abundance of water in the planet's early history, the main building block for life.
First of all, we want a landing site that is ancient, because the hypothesis is that conditions on the surface of Mars 4.3 to 3.9 billion years ago were similar to those on Earth when life started here. So the site has to be old. The second condition is we want a site where we had liquid water present over hundreds of millions of years. And we want this liquid water to be what we call low energy or slow flowing water, like on the canals in Amsterdam.
The rover then scouts around for the ideal locations and, with its driller apparatus, digs deep into the Earth to extract soil samples, which will be placed into its onboard chemical analysis equipment, hoping to find ancient signs of life. Beginning this year, the next wave of spacecraft begin their sojourn to the Red Planet. NASA's InSight mission, the first to be launched from Vandenberg Air Force Base in California for another planet, is preparing for liftoff. The vehicle had already been through its pre-flight test and had been shipped to the launch facility. It is crucial that all aspects of the lander are in perfect operational readiness. The probe is destined for the equatorial region of Mars and will look deep into the heart of the planet.
The InSight mission is a geophysical mission to Mars. It's going to go to Mars and take its vital signs. It's going to take its heartbeat, the seismic activity of the planet.
So we're going to be doing that using a seismometer, a very high precision seismometer, using techniques that have been well developed on Earth to get the understanding of the crust, mantle, and core, and sort of the relationship between those.
Going to take its temperature by measuring the thermal gradient of the surface, which tells how much heat is coming out.
We also have a heat flow probe, we call it HP cubed, and what that does is it's going to basically take the temperature of Mars, and from that it'll be able to understand what the thermal flux is over the course of a full Martian year.
And it's going to sort of measure its reflexes by looking at how the rotation wobbles with the tidal effects of the sun.
Our final experiment is called RISE, and that's going to be looking at basically the wobble of Mars to help understand what the core size may be in composition.
InSight isn't just a Mars mission, it's really a mission to the terrestrial planet interiors.
So Mars is kind of the Goldilocks planet. It's not too big, it's not too small, it's just right. If it was too big, it would have retained a lot of activity and erased all the evidence that we're looking for. If it was too small, it never would have undergone the same processes that formed the Earth, and so it's really just right.
Mars will give us this insight into early planet formation and early planetary processes.
Understanding the details of the structure of the interior of Mars will allow us to address questions of planetary formation that we've only been able to guess at before.
We are missing cold, hard data, and this is what this mission will provide.
Meanwhile, NASA, ESA, and the Russians are continuing their programs. Soon, new missions from China, Japan, India, and the United Arab Emirates will begin. Getting humans to Mars is the pressing goal of NASA and other adventurous parties. Many big aerospace corporations contractors have all been at the drawing board working out the immense engineering and logistical challenges. They all concur that to get to Mars, you need more than a big rocket. NASA's SLS and Orion spacecraft are only two of many components that will be needed. With some more political emphasis, NASA, in concert with other agencies including ESA, Canada and the Russian space agencies, are able to push ahead with the Gateway Facility concept. Effectively building a space station in cislunar orbit between the Moon and Earth, it would be a staging post for a return to the Moon, the gathering of resources from the lunar surface, and an assembly point for a Mars flight and beyond. Orbital ATK is one of 6 companies selected for NASA's Next Step 2 program, a public-private partnership for commercial development of deep space exploration. Not the first to suggest the Moon be a staging post, Orbital ATK recommends a parking orbit in cislunar space built from its successful Cygnus cargo craft. First, they will launch an initial habitat module aboard NASA's heavy-lift SLS rocket with a crewed Orion capsule. Placed in a parking orbit, it will act as a platform for experiments and serve as a destination for future crewed missions. By 2025, additional modules would be added to the habitat, allowing deliveries of crew supplies and experiments, and serve as a waste disposal vehicle at the end of their missions. The modularity of the system also allows for multiple visiting vehicles, providing a base for lunar sorties. Mining for resources, in particular water, would allow for more cost-effective and longer duration missions to Mars. From water you gain hydrogen for fuel, oxygen as the oxidizer, and for breathing, and of course, drinking water.
We have places on Moon which are, at least especially at the South Pole, which has permanent darkness, where we can find water, and we know from some missions that there is water. Water is a good source to produce hydrogen and oxygen. And also to go into the shadow of the Moon, we will have places where we don't have the radiation coming from the Earth. So building a telescope over there by using the material we find on the Moon, so not bringing all the stuff from the Earth, that could also open new possibilities to look deep into our universe.
These crewed missions would also help with man's understanding of how we can best survive long-duration space exploration. By 2030, with additional modules, the habitat could be expanded to provide a Mars transit capability for demonstration expeditions lasting 1,000 days or more. Boeing, the primary contractor for the SLS rocket system, believe their plan will require 5 or 6 SLS launches to be able to get to Mars.
So we want to make sure that we've checked everything out and that we know that it's good to go before we actually leave for Mars. Because once we leave, we can't come back for over 2 years. And the reason for this is because it's the alignment of the planets. The way the planets revolve around the sun, it allows a window of opportunity to go from Earth to Mars basically every 2 years. Just to get to Mars before you even land or anything is going to take 7 or 8 months. The reality is you're going to be there for a year waiting until that window opens up to come back. And then it's going to take 7 or 8 months to come home.
Having a cislunar outpost enables international partnerships and commercial opportunities, such as exploration of the lunar surface and scientific and technological research. After cislunar space, we'll start the actual missions to Mars. The first mission will be to Mars orbit. This mission will teach us about the space systems that will take us to Mars and back. The next mission will send humans to the surface of Mars. The crews will undertake detailed scientific research and investigation. They will start to unlock the secrets of Mars.
Their initial concept, now under development, consists of a power and propulsion bus to provide electric power and propulsion, 2 habitat modules, an airlock module, and a logistic work module, then supplied by cargo and crewed modules from the US and Russia. And finally, it could be used as the vehicle and habitat for long-term exploration of space. Lockheed Martin's concept for transporting to Mars has resulted in a holistic view of the mission. They too will assemble the space gateway in cislunar orbit. This will provide the platform to build the Mars Space Base Camp and get it ready for flights to Mars. They see that Orion is a part of a larger system that provides the supplies and the scientific equipment needed for the journey. This resulted in what they are calling Mars Base Camp. Mars Base Camp is an orbiting mission with 4 main sections and 2 of almost everything for backup. 4 large commercial solar arrays to generate electricity to power the spacecraft. For propulsion, we have 2 cryogenic stages, one either end, and 2 tank farms to store the fuel and oxidizer. Within those stacks lie 2 habitat modules and a large central living space to eat, sleep, and exercise. Most importantly, we have Orion. It is the command deck with all the avionics, navigation, and communications. Orion makes the spacecraft more reliable and gives the astronauts a safe ride home. The orbiting crew could also investigate the 2 moons of Mars, Phobos and Deimos, deploying landers or robots for sampling, even astronauts to explore the surfaces of these moons. The main mission, however, will, after careful examination, confirm a landing site for the next mission and the first human landing. From orbit, the astronaut scientists will have access to the entire planet's surface for rovers and drones to be able to make real-time decisions about where to go and what to examine, retrieving samples from the surface for study. Lockheed Martin's concept, the almost retro rocket ship, the MEDV Lander, is their design for a reusable launch and landing vehicle and is based on the current technology, including the Orion and shuttle systems, and not as far-fetched as first thought. Reusability and innovation will conquer Mars. Keeping costs down will make it viable, and making it doable is innovation. That's something that SpaceX is founded on. Their BFR is the direct Mars transport system, from liftoff on a reusable booster, a short time parked in low Earth orbit for a fuel top-up, then direct to Mars and a 3-month cruise, then landing directly on the surface of the red planet, ready to be refueled from local resources for the return journey, landing back on Earth in the one reusable spacecraft. In the meantime, SpaceX is testing its Falcon heavy rocket system in preparation for its maiden voyage. One of the issues of flights to Mars, which is addressed in part by the BFR, is the cruise time. In theory, SpaceX has it down to 3 months. The other NASA-led systems will take 7 to 8 months, a long time to house, feed and power a crew with little to do. Getting there much faster would be a game changer. One possible way to achieve this is nuclear power. Nuclear thermal propulsion, or NTP, could enable faster transit time both to Mars and beyond. NTP is powered by nuclear fission. How it works is conceptually simple. Energy from fission is used to heat a hydrogen propellant to about 2,420 degrees Celsius. This hydrogen is then accelerated through an exhaust nozzle, resulting in a propellant efficiency roughly twice that of the best chemical rocket engines. For example, it may be possible to fuel modern NTP systems with low-enriched uranium instead of highly enriched. The physical size of an NTP engine is largely determined by the rate at which fission energy can be transferred to the hydrogen propellant, but the equivalent volume of the uranium that would be split is actually quite small, roughly that of a toy marble. Getting travelers to Mars faster, NTP can take months off the trip compared to using traditional chemical systems. This would reduce the need for payload, food and power for the crew, minimizing the risks associated with exposure to galactic cosmic radiation, microgravity, and other hazards of deep space travel. The maturation of nuclear thermal propulsion will also promote the successful development of the kilopower fission power systems for use on the Moon, Mars and other destinations, as a main source in situ for life support, communication, industrial and other diverse applications. Harnessing first-generation NTP systems is a first step towards advanced nuclear propulsion systems capable of travel throughout the solar system. New projects are advancing slowly, moving hardware into the testing phase, new designs, new capabilities. The next 12 months will see an intense rise in flight tests, demonstration launches and high-priority flights. Some are on time, others are not. Let's check the flight status of some of this new hardware and these new capabilities. Early morning at Armstrong Flight Research, Edwards, California. The Sierra Nevada Corporation's Dream Chaser sits engineless, awaiting a lift from a chopper. Lift and release. The remotely controlled lifting body makes an unpowered descent to the runway, completing another test run. The 10-year project has had its difficulties, but now the pilotless cargo ship is a step closer to a 2020 launch with cargo to the ISS. Boeing's crewed capsule, the CST-100 Starliner, has survived several high-altitude drops testing chute and airbag deployment. Weight and aerodynamic issues have pushed testing back by 8 months. Other aspects of design, however, are proceeding well, including new spacesuit designs.
We needed a suit that was airtight, could withstand the pressure differential, could get the crew down from an extremist situation, whether it was a fire or a cabin leak.
Underneath these shoulder covers is some material that we've developed that really helps provide pressurized mobility while still preserving unpressurized comfort.
You can pretty much lay there without any external cooling, right? It's that comfortable. It's something that I could stand here like this in and not have to worry about developing a big heat load.
The gas intake valves are located on the abdomen for easy access. The lightweight gloves and connections allow easier attachment and come with added technology.
A neat feature about these gloves is they have a advanced material here that enables you to interact with a capacitive touchscreen. So any type of tablet you'll be able to interact with while wearing these gloves while suited fully up in the suit.
The lightweight helmet, akin to the Russian Sokol design, is attached to the suit and sealed with a zipper. The suit is designed to be worn in the capsule and not for EVA purposes, and only comes in Boeing Blue. At the same time, Boeing has the capsule trainer in service, and NASA astronauts assigned to the commercial crew roster are getting a taste for the new capsule.
What the part task trainer does is it gives you a chance to get the feel and look, where to look, how to use the procedures. When you go to a screen in the background, when I hit this button, what's it going to look like?
So I think one of the greatest things about these trainers, it gets you so used to what you're going to do. You will practice a number of times that you'll be so familiar that, like a lot of people ask, is it scary? Of course it's scary because you're sitting on a rocket, but you're very familiar with where you are.
Test schedule calls for an uncrewed orbital test later in 2018 and a manned flight at the end of 2018. This is very ambitious, however, and previous experience of spacecraft engineering suggests it may be 12 to 24 months premature. Another company with an ambitious timetable is SpaceX, whose Dragon capsule is looking for an uncrewed flight early 2018 and a manned launch 4 months later. The new breed of entrepreneurial and commercial imperatives may just make it. The interior design of this capsule is more in line with high-end sports cars. Maximum use of carbon fiber, titanium, and other lightweight alloys, coupled with the latest in electronic display and glass control surfaces. Far more commercial in feel than the usual NASA or Russian practicality and minimal comfort ergonomics.
50 meters per second. Slightly below nominal. We're over 1 kilometer. Trunk deploy. Chugs look good. Sequencing the mains.
Their capsule is well along its testing phase, having completed both static and pad abort exercises, including parachute deployment test. A wild ride indeed. With room for a crew of 7, the Dragon capsule may well be the first commercial entity to launch and land astronauts from the ISS within a year. Unity spaceplane of Virgin Galactic has been building its test credentials slowly but steadily. Having suffered catastrophic failures in the past, they are fully focused on safety. Ground crew operations of both the spacecraft and its carrier plane are rehearsed ad infinitum, training and checking as flawless procedures evolve. Motor testing again and again. Unpowered flights, carried aloft by the White Knight 2. Rehearsing with ever greater complexity, the latest flights fully loaded with rocket motor and propellant tanks. The pilots performing a perfect landing. Next step, a powered suborbital flight, perhaps sometime in the next 12 months. The newest space-capable nation, New Zealand, is preparing the second launch of its Electron rocket. Powered by Rocket Lab's homegrown 3D-printed Rutherford engine, their second test launch is imminent, designed for the small satellites in low Earth orbit at a fraction of the standard cost. If this second test launch is successful, then Rocket Lab may drop the third and final test flight in favor of full commercial deployment next year. Blue Origin's reusable new Shepard rocket and capsule system has proceeded successfully through the testing phase, including launch abort and single parachute landings. It won't be long before 6 paying passengers will fly into space.
New Shepard has cleared the tower.
There it is, 70,000 pounds of thrust pushing that crew capsule.
Okay, so those 3 mains are reefed right now to keep them small. The reefing will remove shortly to fully expand, as you can see.
And touchdown of the New Shepard crew capsule.
Blue Origin is also developing a multi-stage version to reach orbit. The new Glenn could send payloads or passengers into orbit with a 2- or 3-stage variant, although it is still some years away. Delayed several times from an over-enthusiastic launch timeline, the Falcon Heavy will undergo a static fire test of all its 27 engines in the coming weeks. The first test flight will follow within the first 2 or 3 months of the new year. NASA's Space Launch System has hit further snags in development, namely issues with the welds of the enormous fuel tanks. Not unexpected, as the new technologies and manufacturing techniques evolve. Delays in delivering the Orion's EMS propulsion system have also set back the timetable, with 2020 likely to be the earliest a flight could take place. The James Webb Telescope has also been delayed by a year. A planned Ariane 5 launch will hopefully take place mid-2019. Ariane 5, Soyuz and Vega launches are due for an upgrade. At the European spaceport in Kourou, French Guiana, the new launch facilities for ESA's Ariane 6 launcher are being built. At least the big hole is there, the excavation is done, and the launch zone buildings will soon appear on schedule.
The independent access to space is, of course, the primary objective. And we always used European developed launchers to fulfill this objective. We were lucky enough that we were very successful also on the commercial market with Ariane 5. We still have over 50% of the commercial market. As we all know, this environment is exposed to fierce competition. The offer of launch vehicles from 2020 onwards will be significantly higher. And we have designed Ariane 6. We have designed it to cost. We have designed it to be able to go against this fierce competition in 2020 onwards. And for this, of course, we also use this launcher to deploy European flagship programs like Galileo.
This move is associated with a change in the governance of the European launcher sector, based on a sharing of responsibility, cost and risk by ESA and private industry.
We are in the middle of the full development of the launcher Ariane 6 and of the base, which is ELA-4 in Kourou. I can say that currently everything goes well. It's on track. We are now in the situation where the configuration is clear. We know exactly what the configurations are with the Ariane 62 and the Ariane 64. The first one is for institutional payloads mainly because it's a single payload version where we can launch up to 4.5 tons in a sun-synchronous orbit. And the Ariane 64 enables a dual launch, which goes up to 10.5 tons in an equivalent geostationary transfer orbit.
ESA and its member states have a new role in Ariane 6 in the sense that we change governance. Governance by giving more responsibility to industry, to the private sector, while the public sector has defined the high-level requirements, which means that we said we want a cheaper launcher, we said we want an environmental friendly launcher, we want a flexible launcher, and this is absolutely key in the current situation to be ready to catch new markets, and Ariane 6 will be the right response to that. We can say that European industries are working full speed ahead. We just had maturity gate 6, what we call, where we can consolidate the industrial structure. We aim at starting the first batch of production next year, spring next year. So now we can say the industries are ready, they are full speed ahead, and we will start to produce Ariane 6 from next year onwards. It is very clear, in a definition of a space power, the independent access to space is part of it. Ariane 6 and Vega C is the new family of the European independent access to space.
Vega C will cover the deployment of the Sentinel satellites for the EU's Copernicus program. Vega C will increase Vega's current capacity from 1.5 to 2.2 tons on polar orbit, which is the most common for observation satellites. For Ariane 6, the pad will be different from previous launches in Kourou, with a horizontal preparation of the stages. The first launch is still on target for sometime in 2020. Although there are extensive works going on at Kourou, they will not affect the upcoming Vega launch of the European Aeolus satellite, slated for early 2018. Next major launch is the TESS exoplanet survey mission. The satellite has completed pre-flight tests and is the first NASA astrophysics satellite to be launched under contract with SpaceX. The current launch window of the Falcon 9 is no earlier than March 2018 and not later than June 2018. The second exoplanet hunter, Cheops, is on schedule as well.
The satellite is commissioned by ESA. The project is being led by the University of Bern. They also built the instrument. That's the main part of the satellite. And the satellite structure, the platform with all the housekeeping, is built by Airbus in Madrid.
The satellite has gone through rigorous pre-flight tests, including vibration, acoustic and vacuum chamber tortures, and is on track for a late 2018 launch aboard a Soyuz launcher.
Gaz hume avec AM. Allumage triétage. À tous de DDO. Attention pour le décompte final. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, top. Et décollage VS12.
Bepi Colombo, the joint JAXA-ESA project bound for Mercury, is ready to launch. The mission consists of multiple parts, including the Mercury Transfer Module, a sun shield, and 2 scientific orbiters, ESA's Mercury Planetary Orbiter and JAXA's Mercury Magnetospheric Orbiter. The spacecraft was assembled in its launch configuration inside a clean room at the European Space Research and Technology Centre, or ESTEC, in Nordwijk, in the Netherlands. It has been dispatched to the spaceport in Kourou for its mid-2018 launch and 7-year flight to Mercury. The tenuous envelope of gas surrounding our planet is an unbelievably complex machine that protects us from the vacuum of space, shelters us from harmful radiation, and allows us and the biosphere to breathe. It is our atmosphere, and we need to learn much more about it so we can take better care of it. Soon, the European Space Agency ESA will launch its new Earth observation satellite called Aeolus. Using cutting-edge laser technology, Aeolus will provide near real-time observations of wind profiles across the globe. These will improve the accuracy of numerical weather prediction and climate modeling, and advance our understanding of global atmospheric dynamics.
Aeolus is one of the Earth explorers that is going to look at the Earth, trying to understand the wind profiles globally. And that's a first, it doesn't exist yet. The whole idea was that we only have wind measurements on very different small spots on the Earth, and we didn't have it globally. So the mission scientists had been asking for this because it's a gap in our measurement system.
The mission aims to expand our knowledge of our atmosphere and weather systems. Aeolus will achieve this by providing global observations of wind profiles from space, providing data which has never been available before.
It's unknown ground. It's what we call uncharted territory. So we are the first agency trying to get a satellite in orbit that looks at the Earth with a laser and trying to understand the wind profile, so the direction, the height, and the wind speed. and therefore improving the weather forecast. Because nowadays we only have at single points balloons that measure the wind, or airplanes that give us some data, or at fixed points, at discrete points. This will look down to the Earth in a polar orbit, will dump every 90 minutes the data to Svalbard. That will be distributed to all the European meteorological institutes. And then when you're sitting at home on your couch, you watch the television and you see a weather forecast that is much better than we have it today.
Aeolus will fly in a sun-synchronized polar orbit 320 kilometers above Earth's surface. Its data will be sent to ESA's Svalbard ground station, located in the archipelago halfway between Norway and the North Pole, every 90 minutes. The satellite's main instrument is Aladdin.
Yes, the way the Aladdin instrument works is to eject an ultraviolet beam down through the atmosphere, and then particles of moisture in the atmosphere at various levels are in motion because of the wind, and the system measures the backscatter from those particles using the Doppler effect and can detect the wind speed at the various altitudes. And that's the way the system operates.
The development of Aeolus has been a long and difficult process, with new and cutting-edge technologies designed, developed and tested on the ground.
It has been a very difficult challenge, let's say. It's a long life, because it exists already for 16 years, the program. And when we first had the part of the instrument, when we switched it on, it worked. Then we put it in vacuum and it stopped working. And no one had realized that we needed oxygen inside the satellite to keep the laser active. So it was quite a challenge, so we had to develop a whole new set of techniques. It's maybe a bit too detailed to go in all the details, but as a lot of technology has been developed, put in this nice little satellite which is behind me.
Aeolus is another ESA Earth Explorer mission aimed at pioneering new technology while providing useful data about our ecosystem. It showcases the technological expertise of the European space industry and ESA's objective of monitoring and understanding the planet we all live on.
The main challenge for us has been within the development of the Aladdin instrument. There's a very high-powered ultraviolet laser system in there that is an inherent part of the instrument. And the technology behind that laser system, the development of a stable laser, high-powered laser beam, and the optics that then focus and divert that beam through the system is very critical, and that's been a very key part of the development. After many years and much hard work across the European industry, we've overcome those problems. We've got some new development through coating technology on the optical surfaces to protect them. And we've now got a stable system that's been fully tested on the ground, and we're ready to go.
The tracking of air pollution is also part of the European Union's Earth observation program, Copernicus. One of the satellites that gave scientists massive amounts of data on atmospheric pollution was Envisat. This satellite used several spectrometers to detect ozone and trace gases in our atmosphere. The latest satellite, the Sentinel-5 precursor mission, was recently launched and builds on that legacy of Envisat.
So we started this precursor mission because the scientists wanted continuity of data. At the moment, we only have one spacecraft doing that job for us, which is OMI, and OMI is coming towards the end of its lifetime. The next missions that will do this job is Sentinel-4 on metopside generation, which will only be launched in early 20s. In the meantime, to ensure a continuity of data, we need Sentinel-5 precursor. It will be the only such mission doing this job until then.
Sentinel-5B is a precursor to the Sentinel-5 mission, which should be launched around 2021. But it's not only a precursor, it's also a gap filler, because it's filling the gap based on the data that we have coming from Gomez, Kirmaki and OMI measurements towards this future Sentinel-4 and Sentinel-5 missions.
Sentinel-5P is the first atmospheric chemistry mission within Copernicus. Its main instrument is a state-of-the-art spectrometer called TROPOMI, which will be used to detect trace gases in our atmosphere. The Sentinel-5P satellite is a timely replacement for the ERS and Envisat after it stopped working. There was an urgent need to fill the gap in observing air quality and air pollution. Furthermore, according to the World Health Organization, air pollution is responsible for over 3.7 million premature deaths worldwide every year. But the health costs are even greater, as many people suffer from non-lethal afflictions either caused or aggravated by breathing polluted air. Another major health concern on which Sentinel-5P is gathering data is the ozone in our atmosphere. When that ozone is depleted, ultraviolet light from the sun is no longer filtered. Increased exposure to UV light can cause skin cancer, immune system damage, and other ailments in humans.
The tropomi data will be used operationally, so it will be used to improve the air quality forecasts. And air quality forecasts are of course important for people who are vulnerable to pollution, but also for the general public in case of big smog events. What we can do with the tropomi data is we can look at the emissions of pollutants, and when you see them changing over time, that is very important because we can see if certain policy measures have the right impact, or where we see still increases and still have to do more to reduce the polluting emissions.
A decline in air quality, such as smog, poses massive risks for people's health. And one of the main contributors to climate change is the pollution of our atmosphere by greenhouse gases such as CO2 and methane. This is why measurements on air pollution need to be undertaken everywhere. Like here, for instance, with a mobile measurement station at the University of Bremen. It detects smog and industrial emissions. These local measurements supplement and validate the global observations from satellites, which in turn are needed for scientists to study the air we breathe and the planet we live on.
Well, the satellites are a key information base and knowledge base for the study of atmospheric physics, chemistry and meteorology. It's essential data because we need to know not just what's coming out at a given place, but we need to know where it's going, where it's depositing at the surface, how it's being transformed, is it going to be taken up by clouds and rained out, if so where? And this whole transport and transformation process is a complex business. In general, we have this problem of unambiguously identifying anthropogenic impact from natural phenomena or natural behavior in this complex system and how we're modifying it. So this is the challenge for the science, which is a necessary prerequisite to enable good legislation and ultimately sustainable development. So in this context, measurements from space are essential because they provide us with the global picture, or from the local to the global scale.
The Sentinel-5P mission will have quite some improvements as compared to previous missions. For example, if we look at the spatial resolution, we will break a record, namely we will look at city scale because the nadir pixel size will be as low as 3.5 kilometers times 7 kilometers. So we can then investigate small-scale features over big cities and city agglomerates, for example.
The mission will monitor the atmosphere using the tropomi spectrometer to monitor various trace gases in our atmosphere and reduce data gaps between Envisat and Sentinel-5. By combining satellite data with the local measurements on the ground, scientists can properly monitor air pollution and how it impacts us and our planet.
We have lots to understand to assess the impact. Ultimately, more pollution is bad for health, bad for people, and the estimates are somewhere between 3 and 7 million people a year die prematurely from air pollution. This is a large number of people.
At the forefront of Earth observation, the European Space Agency helps us to understand climate change and pollution by giving scientists and policymakers the data that can drive legislation.
These atmospheric measurements are extremely important for mankind.
First of all, to see how our planet changes in terms of climate, but also to see how air quality changes in different places and over time. We have highly polluted areas, which are, of course, transporting pollution from one place to the other. So these fluxes of pollution or gases is very important to monitor. But also, if you take Europe, for example, Europe has introduced very strong legislation and regulations in order to reduce greenhouse gas emissions. And this has also to be verified, and these satellites are a very good measure or very good way of making sure that these reductions are taking place at a large scale.
In the early 2020s, the space component of the Copernicus atmospheric services will be extended through the addition of Sentinel-4 and 5 missions. Sentinel-4 will be a geostationary mission, whereas Sentinel-5 will be a low polar orbiting mission like Sentinel-5P. Atmospheric services are part of the Copernicus portfolio, which comprises 6 main themes: marine, land, emergency, security, climate, and atmosphere, giving a complete overview of our planet's health and its evolutions.
Can have a lot of practical applications using the data from the Sentinel-5P mission. One idea would be perhaps if we look at the harmful UV radiation, you could set up UV radiation services so that people on the street, so to speak, in the sun like today, could inform themselves how harmful it is to receive this short-wave ultraviolet radiation.
The Sentinel-5 precursor data will be combined with models and other data to develop targeted services, and they will be available as apps, social media information, or web services, so that a lot of people can choose their way they want to be informed about the environment.
Atmospheric measurements are important because especially these measurements that are done by Sentinel-5 precursor, like tropospheric ozone, information about nitrogen dioxide, sulfur dioxide, also information about aerosols, particulate matter, they have impact on the health of people. They can impact the people who have problems with their hearts or with their lungs. And as it has been shown, there are more than 400,000 premature deaths in the European commissioning based on exposure to air pollution.
Air quality in Europe in particular, but also in the US and in Japan, got much better over the last years. That's a really big improvement. And at the same time, air quality in the developing countries, in particular in Asia, has gotten worse because they use much more energy nowadays, and that's a big source of air pollution. Also, if they are using more cars, that will pollute the air more. So it's different, depends on where you live. In some places air quality gets better, in other places air quality gets worse. I should add that in the last 3 years, air quality in China has improved because they are very ambitious about that and have very strict rules. So they are trying to follow the European or United States path in improving air quality with better technology.
Observation from space is just one of several methods of measuring atmospheric pollution. Satellites provide the data, although they need to be calibrated with measurements on the ground.
So we are offering a comprehensive analysis, integrating data at different scales. So we are using observations, we are combined with modeling, with satellite data, and all this information is complementing each other. This is the good thing of this kind of analysis. Satellite have the advantage of providing a global picture. Trends, you can study trends very well, how the main flows are, taking place. But satellite data, they don't have the resolution to get in detail in the individual processes. So here, with our in situ measurements, we are getting in one particular point, and we get deeply in the detail.
The satellite gives these beautiful maps, but you can only use them really if you have a validation measurement to compare to, and this needs to be a very good measurement, and this needs to be taken on the ground. That's very important for us because we need to be very confident of the satellite data. And once you have launched the satellite, it's out of your hands, and you cannot bring it to the lab and double check and test it. It's there, and you need to trust the data. And the only way to get this confidence in the data is by comparison to other measurements.
Other forms of atmospheric pollution, such as the exhausting of carbon dioxide, methane, and ozone, contribute greatly to climate change.
Well, I think basically it's often the case that our models, which are extremely complex and good tools, often don't necessarily have the right physics or chemistry in them to be able to predict what's going on in the future. So a lot of the time in atmospheric science, we've been making discoveries. Back in the late 19th century, early 20th century, the discovery of the stratosphere was a complete surprise at the time, or fairly surprising. The fact that temperature increases above the tropopause. This was a surprising discovery, and really that's been typical. We didn't expect summer smog. We don't understand why in Paris there was a really big smog a couple of years ago in spite of improvements of legislation. This winter we had in London a smog which is maybe being attributed to excessive wood burning recently. So there's a lot of things although we're getting over the last 25 years much better information, but the satellites in particular tell us ultimately, or could tell us ultimately, what the source strengths are and enable us to follow the information, and thereby, together with models, give really good prediction for people about the air quality that they're receiving.
The Copernicus program is very important for Europe and for the world. First of all, the Copernicus program is providing free data to everyone at any place in the world. So many users, not only in Europe, but also in America, in Asia, are using our data in a very large scale and very significantly. So therefore, Copernicus is really monitoring the health of our planet from all dimensions: the atmosphere, the oceans, the land surface, the ice caps, and this whole system of the Earth composed of these components is monitored constantly with Copernicus. And therefore it is really important to see what is the state of our planet and how it will evolve in the future.
Well, the data can be used for different applications. So for example, for the air quality forecasts. It's also used by KNMI, for example, for the UV forecasts. And we also use it to warn the aviation for volcanic ash plumes. On top of that, the data will also be used by scientists around the world to study the atmosphere and to study how man is changing the atmosphere over time. Continuous monitoring is very important, especially when you're looking at slow changes, and an overlap between the data is then really necessary to be able to glue these different data sets together to one data record. And we have data records from these kind of instruments starting in the 19s, for example, for the pollution. It's very important to maintain these valuable data records and to extend them into the future.
Well, the data is important for our climate research and also for our environment, because the air we breathe, it could be changed due to all sorts of pollution events. And then a second example is that we need to monitor our ozone layer. Since ozone is destroyed due to chlorofluorocarbons, Sentinel-5P will have also the role to monitor the further evolution of the ozone layer.
Mankind can halt the pollution of our atmosphere with good legislation. The European Space Agency, ESA, works tirelessly to monitor our planet and the air we breathe.
We need a future where we, with so many people on the Earth, are in a position to maintain a good quality of living for human beings, but also for the biosphere.
Astronauts and cosmonauts, we've seen them train and study for years to enable these select people to work and live aboard the International Space Station. We have seen countless hours of their activities live on television and in the media. With this wealth of experience and insight behind them, what do they think when they return to Earth? Without exception, these spacefarers simply cannot wait to get back into space. Astronaut Paolo Nespoli is on his third space mission.
It's what I call becoming an extraterrestrial person. You know, it's losing your earthling things, and now you are really an extraterrestrial person because you don't think anymore about gravity, you don't think anymore about up or down, you think about what you need to do and position yourself so you can do it in the best way. You need to get used to working, to live first in space, being able to be very confident in the environment where you are. You need to be able to learn to translate extremely efficiently without banging into things. You need to be able to carry stuff. You need to be able to learn how to move around and do things, and how to sleep efficiently, how to work efficiently. And this takes like a month and a half. So after that time, you are fully ready to work, and that's why 6 months, because you have the capability then of performing at 100% of your capabilities, and then, you know, after 6 months, I think people are ready to go back to Earth and, you know, taste again the food, smell the air, see their friends, their family. For me, it was an exhilarating experience. I mean, I found this thing of trying new things. I find it really good. I felt I was like a little kid trying to do something, you know, try to get crazy and get inventive. And sometimes I thought, I should try something like that. And I said, that's not possible. It's never going to work. And then you try it, and you see that it opens up all sorts of other things that you never thought about it. And that it's a very good feeling. I mean, this feeling of discovery. The astronaut in space is one of the resources of the space station, and the control center want them to use as much as possible, so they have to make sure that they can work. In fact, we do work from 7:30 in the morning until 8:30 in the evening. That's the working day, and Houston and the other control center make sure that it's filled with activities. About 50% of that time is used for maintaining the station. We need to fix things, we need to move equipment, we need to change experiment, we need to load and unload space spacecraft. We need to prepare for spacewalks. This is an important part. And then another 30 to 40% is actually scientific work. I am an engineer, an aerospace engineer, but I will do experiments that have to do with genetics, with medicine, with life science, with metallurgy. And we have a complex set of experiments spanning 360 degrees.
Which is a sealed environment. I'm going to open up.
It's a little bit going to school, yes. It's a little bit like the adrenaline that pumps in when you are in an exam, and you want to, from one side, you want to show off. You want to show all the things that you know. In the other side, you need to be careful because some of these things can be very tricky, and it's easy to misunderstand something or getting too much involved in one thing and forget about the other one.
There are currently 16 active members of the ESA astronaut corps. Paolo is among the oldest. At 60, this is his third flight into space.
I feel really honored to be able to fly in space again. It's a very nice experience for me. I'm looking forward to use all of this investment that the agency have made in the past year to qualify me, all the personal investment that I made in get qualified and stay qualified, and use it again, go to space and be useful. I mean, I'm 60, but I'm going there and I'm expected to perform as anybody else and carry out my task, and I'm looking forward to do what is needed and possibly a little bit more.
Other ESA astronauts who have experienced their first missions in space are already in training for their next. Alexander Gerst has spent 165 days in orbit with 6 hours of EVA experience. Even though he is well aware of the amount of work and effort that lies ahead, he's keen to get back into space.
It's a fantastic feeling to be back in training, of course. You can see the training facilities right behind me, and you can see why it's so interesting. I mean, this is like a full-on mock-up of the space station, so this is really the closest you can get on this planet to how the space station feels and looks like. And I've, of course, missed it a little bit after my last mission. I returned in 2014, that's 3 years ago, so it feels great to be back in that working mode.
He'll certainly be continuing some of the research he started in orbit back in 2014. On top of this, he'll be fulfilling a new role, that of ISS Commander, a job which requires a high level of responsibility for the station and its crew.
Of course, a new part to my training is that on my next mission I have the added responsibility of being the ISS commander, and to me that's a great honor. So I'm very humbled by the trust that people have in me to actually command this fantastic space station. But of course, it comes with a big responsibility also already in training. So that means I'm right now not only responsible for my own training, like in my last mission, I had to make sure that I'm trained and I can do everything that people need from me in orbit. Now I have a crew to take care of.
Another key element of the returned astronaut's life is to impart their considerable experience in order to help train the next rookie astronauts. Matthias Maurer, ESA's newest astronaut, has been training with astronauts Tim Peake and Luca Parmitano, both of whom boast extensive EVA experience.
It's actually a lot of fun because I can relate what I'm doing on the ground to what I did in orbit. And it gives me perspective to how it's going to be while I train. And as a matter of fact, our feedback to the instructors is very well received because we can improve the training that we receive just by getting our experience into the equation.
It's great to be back in Houston training again. I'll be in the neutral buoyancy laboratory very shortly with Matthias Maurer, the German astronaut, so my ESA colleague. Really looking forward to that as well, trying to sort of impart some of my knowledge from my spacewalk and to share my experience with Matthias. Here in Building 9, of course, it's great to be back, reminiscing about my time on the space station, but also learning about the new developments that are constantly changing on board the space station.
Don't tether to this D-ring on the bottom. That's only for the battery. The other thing, too, is that you can shove this all the way in here and then on this foot.
I have so many fantastic images and wonderful memories of my 6-month mission to space. If I was to have to choose one highlight, I would probably say the spacewalk was the highlight. Just going out of the hatch and seeing space, seeing Earth, and looking back at the space station from inside a spacesuit, that really was another order of magnitude over and above just the experience of going into space.
You put your toolbox down here, and your toolbox will stay because the water will keep it and the gravity will keep it. In space, you put your toolbox down, you look back, and it's gone, and it's up there, and it's all over the place. So, and all the tools inside your toolbox will all be floating around a lot more. So, the microgravity is really difficult in space.
I was at the NBL earlier this week, and just seeing the suit-up operations and seeing the suited guys going down for their spacewalk training, it really brings into perspective what the realities of a spacewalk are versus the NBL. And you know, there aren't that many. The NBL really is a fantastic place to train for a spacewalk. It's the best place that we can train on Earth.
The crew hook side?
Yes, and actually, this is a good opportunity whenever you're heading out the airlock.
All European astronauts get training on how to operate in a spacesuit, in the American spacesuit. And so we need to learn how the spacesuit works, how it functions, and also how difficult it is to work inside such a suit. It's very limiting, and like a work that takes us 5 minutes here on the ground, in space it takes me half an hour. And afterwards my entire body aches, and it's hard work outside on the station.
And try to do hand over hand. And Matthias, you don't have to ingress the APFR. We could have drivers.
I pause for a second to figure out which... I hope that I get the chance to do a spacewalk, because all my colleagues told me a spacewalk, it's like the best experience of your space flight. Leaving the station, seeing the station from the outside, and having a very clear picture of the Earth below you without being limited by a window, just looking through your visor. That is, the perfect image, and I'm really looking forward to it. I'm happy that I'm out of the water and that I actually can move my arms again, how my body is designed to move the arms, because the suit constrains a lot of my arm movement.
We thought it'd be a great idea. It kind of serves its purpose, but we found better techniques like safety tether paths.
When you're in there, in that position, and you've got your gravity here, and you've got your gravity and everything, just even to see the unlock. I couldn't see it.
It's good to just have one wire tie dedicated to a bunny ear. Of course, you can pop this down, pop that up. Mine is this direction here. I like the joint to be on top because you'll find in the pool you need this to maintain your rigidity.
This right now is in motor, so in order to do the cal test, you need to either put it in retroclockwise or counterclockwise. There you go. That's a little different. Now you get your LED test, and now you know all your LEDs are working. Don't tether to this D-ring on the bottom. That's only for the battery. The other thing, too, is that you can shove this all the way in here, and then on this foot. It's not new to you. You know that you're going to go ahead and stick your boot into the toe loop, put your heel down.
And foot in, and then I lean backwards. When we were in orbit, we had 3 spacecraft come up. We had Cygnus, we had HTV, and ATV. ATV was all the way aft, and you have to cross all of the Russian segment in order to transfer cargo to the other side. And you would really need some coordination with our Russian colleagues, because if they're working doing sport, then you're floating in the middle of their activities.
So the station does become a very busy place.
Even in shape, there are modules that are in a different position than compared to when I was up there, and the procedures have changed compared to when I was up there. Specifically the emergency procedures, and all of the payloads are different. So all the training has to be done completely from zero.
The seasoned astronauts still get a kick out of looking to the future, especially when it comes to new equipment and spacecraft like the Orion capsule.
Visiting the Orion capsule today was really exciting, and it's the next stage in our space exploration. Europe is very much a firm partner in there. We're providing the service module for the first exploration missions, which is really exciting. Going back to the moon with a vision of using that same vehicle for some form of Mars transportation vehicle.
Currently, we are flying to the ISS, but the ISS program will soon become to an end, or it will become a commercial space station. On the other hand, we are also looking to fly much deeper into space. The ISS flies at 400 kilometers altitude, and with the Orion, we can actually go into deep space. For example, to the moon, which is 400,000 kilometers, so 1,000 times further away than the ISS. And actually, this opens a new perspective into exploration. We will go to the moon, and after the moon, we will go to Mars. And there are lots of adventures, lots of science that we can do in deep space.
Experience isn't the only thing astronauts bring back from space. Their biological specimens help evolve the gastronomical sciences.
Here we are opening the samples we received from Thomas, coming directly from the ISS. There are different samples of urine collected during 10 days of tests.
Providing enough energy for the astronauts is a critical aspect of payload planning, particularly for long-duration flights.
The centre will provide us with an inventory of all the food taken by Thomas up there for all the time of the exercises he made during the 10 days of our tests. Here, for example, we can see on this table the energy consumption of Thomas every day, how much he has spent.
You can't order pizza to go in orbit, so the decisions about what to take with them can be critical for astronauts.
Food is something that's really underestimated down here on the ground. Like, people go like, oh yeah, I'm gonna fly to space, I don't care what food I take. It's not bad. Well, you start caring about that 1 month into the mission, and then if you made the wrong decisions, it's a hard remaining 5 months. This is mainly to trigger my memory for the food that I already had, and now I can make the choices based on how I remember them. And then there's a few new ones in between. For them, I have to sort of guess. There's still debate if the taste actually changes the actual taste buds, if people perceive taste differently. My personal opinion is we don't. I think it's the same, but the cravings change, and that is really hard to predict. Right now, I might not care so much for broccoli and cauliflower, but up there, I really liked it. Because it's pretty protein loaded what we have. We have a lot of meat, and then I tried to add anything that reminds me of something green. Let's put it that way. I mean, those beans, they don't resemble beans a lot, but they actually taste really nice. Oh, we didn't have blueberries last time, right? We had raisins. That stuff is awesome. Last time I got a few Russian bonus containers. They also have very, very good food. Their food is more succulent, like they have more grease in there, also more spices, also more salt, which is not so good for the bones. So I tried not to eat so much of it. The American food or the European food is more healthy, I would say. But once in a while, it's really satisfying to just open a can of this really succulent, savory Russian food, and I absolutely enjoyed it. It's really good. On my last expedition, we tried to have the meals all together. The US crew, European crew together, we always had meals together when we could. And then on the weekends, we would gather, like the 6 of us. Either the Russians would invite us to their segment, or we would invite them. And then we have the big table, and everybody brings something together, and it's kind of this medley. That's important. Those are the relaxation moments. You can take a time, you put music on, and you chat about how your week went. And it's the last thing that I have for today, after a successful tasting of 48 items.
With experience comes cooperation. ESA is now conducting astronaut training activities in China. Samantha Cristoforetti and Ruki Matthias were each teamed with 2 taikonauts, who between them have considerable spaceflight experience.
We are basically practicing what would happen if there was an off-nominal landing. We wouldn't land on the ground, but we would actually land in the water, and we would have to survive independently for some time and using the rescue boats and the rescue equipments and exiting, of course, the re-entry capsule autonomously.
After donning insulation and buoyancy suits, they practiced rescue procedures with both a ship and a helicopter from a mock-up Shenzhou capsule. Space missions can be unpredictable, and training exercises such as these ensure that astronauts are prepared for every eventuality.
The training experience so far is great. The Chinese are really well prepared. It's a high-level equipment. We get helicopter airlifting. We have a huge sea survival rescue ship, which is usually employed on the high seas. So very good equipment and a very good experience so far.
Accompanying Samantha and Matthias in China were an ESA flight surgeon and a training specialist who gained insights into the different cultural nuances and approaches.
During this training, I have had the opportunity to work very closely with our Chinese medical colleagues, and I'm very, very impressed about how they have combined their traditional Chinese medicine, which has thousands of years of history, with the most advanced medical knowledge that we can find now in the world.
Training here is very, very well organized. So we have different ways of approaching training, which is inherited from the ISS program, but actually they are not that far away. So it means that we find common words and common understanding in the way they also organize this training. So for us, it's a very good sign for further cooperation with the Chinese.
This training exercise wasn't the first collaboration between the 2 space agencies. In July 2016, Chinese astronaut Ye Guangfu joined ESA's caving course in Sardinia to experience an extreme environment as part of a multicultural crew. Both activities stem from the 2015 agreement to boost collaboration between ESA and the China Manned Space Agency, with the ultimate goal of flying European astronauts on board the Chinese space station from 2022.
This joint training we're doing here is a first step in a cooperation that we all hope will lead one day in the early 2020s to a European astronaut flying with the taikonauts to the future Chinese space station. And so, of course, I would be thrilled if I had that opportunity.
Organized by the Astronaut Center of China in cooperation with the Ministry of Transport's Beihai Rescue Bureau, this training session has been an important step towards long-term collaboration. Space flight opens up new horizons, not just for astronauts, but for nations as well.
Yeah, so as you know, my last mission was called the Blue Dot. We focused on the view back, the perspective back from space onto our little planet Earth as it flies through the black universe. Now, on the new mission, we decided to take a step further, to even view with a bigger perspective, to acknowledge that it's not only about our little blue planet Earth, but that there's much more out there in the universe. And as the early explorers who sailed, beyond the horizon, towards the horizon, and even further, we named our new mission the Horizons Mission.
We know it's there, and we usually pay it little mind. Yet we notice it when it's not there. Gravity is the all-encompassing force keeping us on the ground, and the planets in their orbits. In space, we are merely cheating gravity, falling just as fast, but missing the ground, an orbit and so-called condition of microgravity. Now, this fundamental universal force is slowly giving up its secrets. Humans live in a gravity field. So what happens when they spend extended time in the zero-G environment, and how can we utilize what we learn to help human beings? This A310 zero-G aircraft is being used by the European Space Agency for research in conditions of microgravity. To obtain zero-G, the plane must perform a series of parabolas. On each maneuver, people first experience almost 2 Gs, feeling twice their normal weight. When the aircraft reaches a specific point,
20, 30.
They inject the plane into the parabola. Everyone on board is then in microgravity.
It's now called out the angle, it's 40 degrees at 50.
Injection.
Injection, that is weightlessness. Here I go. The scientists have 20 seconds of weightlessness to do their experiments behind me. But there will be 30 of these parabolas. So they have plenty of time, 10 minutes in fact,
20.
To do
30.
Their experiments. Time to get down now, because there will be a nasty thud. There we go.
There are 12 experiments on this flight, including 6 by students as part of ESA's Flying Thesis program. The experiments cover everything from fundamental physics and neuroscience to psychology, looking at body image and perception. This experiment is examining the effect of microgravity on the brain. That's important for astronauts doing long-duration stays on the ISS, but there are also wider applications.
We are also interested in people with diseases, for example, Alzheimer's disease or dementia. If we know the mechanisms which are linked of a reduction of cognitive performance and brain activity and where that comes from, we might be able to better design strategies to then help these people.
Inside here is a pulsating heat pipe, potentially a new way of managing the thermal conditions of satellites or components on board the ISS. The copper pipe, seen here showing the flow of a condensed vapor, also has a section made of sapphire that is transparent to visible and infrared radiation.
In this experiment, we're using the infrared camera of the European Space Agency. It's a new camera, high-speed infrared camera, that will be used also on the International Space Station for the next experiment.
After each parabola, there is another 20 seconds of 2G as the plane pulls out to level flight. A few minutes later, the next parabola begins. In between each one, scientists must quickly reset their experiments and prepare for the next bout of microgravity.
This is the only microgravity platform where the scientists get to interact with their own experiment while it is in zero gravity. Rather than doing it by remote on a robotic capsule or sounding rocket, or on the ISS, it's humans, of course, but then it's astronauts doing it, and they can't possibly be as in tune with the scientific needs as the scientists themselves. So this is the only platform that really allows that kind of access, and as such, it's unique.
In the final few parabolas, everyone works hard to finish their science. For the German Mars Society experiment, however, there's only one shot to get this right, as it involves testing the initial deployment of a densely packed balloon that they hope one day will carry instruments for studying Mars's atmosphere. Whether it's preparing for Mars or helping life on board the space station and on Earth, the zero-G plane offers a unique environment for research and the closest conditions possible to being in space. Of course, the ISS is the ideal place to experiment with gravity, or the lack of it. Many experiments are conducted by the crew every day, with new experiments being sent up to the crews in cargo and crew capsules.
Now, you are free to set up as you want. This is just...
Fundamental questions are still to be explained. Most fundamental of all, what is gravity? How can such a weak force dominate the entire universe? How does it keep moons and planets in orbit? It affects everything, no matter what its mass may be. A leaf will fall as fast as a handful of nuts and bolts in vacuum, as tested on the lunar surface many years earlier by Apollo astronauts. It was this man who explained the force of gravity in the space-time continuum early in the 20th century. He theorized that gravitational waves were oscillations in the fabric of space-time, moving at the speed of light and caused by the acceleration of massive objects.
Gravitational waves were predicted by Einstein almost 100 years ago.
A gravitational wave is a ripple in the fabric of space and time. It's produced somewhere in the distant universe and travels across the universe.
When any massive object moves, it's changing the nature of space-time. That's what Einstein told us.
So you have a motion that stretches space in one direction and compresses space in the other direction.
Nobody really believed at the time of the prediction that you could ever detect them because the size of the effect is so small.
It would take multiple massive detectors around the world to sense such a small effect passing through the Earth. Question: how do you detect gravitational waves? Answer: with a Michelson interferometer. This is the GO600 in Germany. Laser light is split and sent along different paths in a vacuum, the longer the better, then reflected back on mirrors suspended on glass threads, completely isolated from any earthly vibrations. The laser light is then brought back together and the interference patterns of the two beams compared. The sensitivity required is astounding.
We literally look for changes in the space-time distance in our instruments as the gravitational wave goes by.
And the gravitational wave pushes them together and apart by 1/1000th the diameter of the nucleus of an atom. No wonder it's taken so long to pull this off.
The first detection was made by LIGO, two detectors a continent apart.
We have observed gravitational waves from two black holes forming a larger black hole.
They're moving at the velocity of light, damn near that velocity. 30 solar masses moving that fast. I mean, they're putting out incredible amounts of energy.
And when they collide with one another, they produce a bigger black hole, but they also produce gravitational waves. And in that process, about 3 solar masses just disappears and goes into gravitational waves.
September 2015 confirmed Einstein's vision of the waves and allowed a fascinating and unique view into the dark side of the cosmos, creating a new science, gravitational wave astronomy. Gravitational waves carry information that you can't obtain any other way. Massive events like a supernova, 2 neutron stars colliding, even the universe creating Big Bang itself, have all produced gravitational waves. These can now be detected, adding pieces to the jigsaw picture of nature and the forces that define space-time. Barely 2 years later, another scientific milestone was reached. Astronomers using a fleet of ESO telescopes have observed a visible counterpart to gravitational waves for the first time. A kilonova from merging neutron stars. August 2017, the LIGO facilities, in collaboration with their European counterparts dubbed Virgo, together detected gravitational waves rippling through the fabric of space-time. Just 2 seconds later, 2 space telescopes from ESA and NASA detected a short gamma-ray burst coming from the same general area of the sky. This coincidence had never been seen before. Astronomers hoped this was not just a coincidence, but another indicator of this cataclysmic event, 2 neutron stars combining in an explosive merger. If scientists were right, then a visible light counterpart known as a kilonova would be expected to follow, revealing the exact location of the source of gravitational and gamma rays. The hunt was on. ESO and ESO partner telescopes in Chile joined other observatories to search for a new light source. They were looking for a needle in a haystack, a faint new glimmer amid millions of stars. But amazingly, they found it just a few hours later, in the galaxy NGC 4993, 130 million light years from Earth. Neutron star mergers are the furnaces where most of the chemical elements heavier than iron are forged. The kilonova, an event 1,000 times brighter than a typical nova, spreads the newly formed elements, including gold, platinum, and uranium, into the surrounding space. Such an explosion had never been confirmed before, but here was one that could be studied in great detail. The ESO observations revealed an extraordinary and rapidly changing event, closely mirroring theory. Heavy radioactive elements were shot into space at 1/5 the speed of light. In just a matter of days, the kilonova's color changed rapidly from blue to red, faster than any other observed stellar explosion. This event marks the start of a new era of multi-messenger astronomy. For the first time in history, we can now combine light signals with gravitational waves, providing a totally new way to probe the universe. The advancement of gravitational wave detection didn't stop there. Talented engineers and scientists set about developing even more sensitive detectors that could be mounted in space, free of nagging earthly vibration and detector size limitations.
5, 4, 3, 2, 1, top, allumage et décollage de VV06.
A proof of concept mission, the Laser Interferometer Space Antenna, or LISA Pathfinder, was launched to test the feasibility of a space-based gravity detector. LISA Pathfinder was launched from Kourou, French Guiana, aboard a Vega launcher into a slightly elliptical parking orbit. Using its own propulsion module, it progressively expanded its Earth orbit over a period of 2 weeks before the cruise phase to its operational orbit at the first Sun-Earth Lagrange point, L1, 1.5 million kilometers from Earth towards the Sun. The science package was built around 2 identical gold and platinum cubes, each floating free in a vacuum. They act both as mirrors for the interferometer and as inertial references for the drag-free control system. A disturbance reduction system, or DRS, was supplied by NASA and consisted of 2 clusters of colloidal micropropulsion thrusters and an electronic unit containing a computer with associated drag-free control software.
So to me, the highlight of LISA Pathfinder is the very first day we turned it on, because we didn't expect the performance to be as good. We thought we would be close to what we have to do, and then we would improve it. We would think about what we have to do, we'd fix things, and it would get better. On day number 1, it met requirements. What it showed us is that this is a very complex type of instrument, but it's doable, and industry now have the experience in how to make a mission like LISA and LISA Pathfinder.
These signals are very, very tiny indeed, and we've been able to show with these test masses inside the LISA Pathfinder satellite that we would be able to see gravitational waves in the frequency band where we're interested in.
I think LISA Pathfinder is already demonstrated that it's possible actually to place 2 test masses in free fall in space with a residual relative acceleration at the level required for the future gravitational wave detector.
LISA Pathfinder confirmed the technology for a space-based gravitational wave detector even before the science operations began.
So a space-based detector like LISA is looking for low-frequency gravitational waves. And by low frequency, really we're talking about very big objects which are in motion. So we're looking at the centers of galaxies, the supermassive black holes at the center of a galaxy, and when 2 galaxies merge, the 2 black holes eventually form one big entity. And it's in that merging of the 2 black holes is what we're picking up through LISA.
Proving this type of technology in situ is a big leap forward in detectors.
It has worked flawlessly, and our performance is better than we could ever have dreamt. Even on the very first day, we had met our requirements, and since then we've just made it better, and it's just wonderful to see how well this instrument is performing. The success of LISA Pathfinder demonstrates that we now know how to build a mission like LISA, and over the next months and years, that mission will now start to be in the design phase, leading to a launch in the late 2020s or 2030s. Gravity is the fundamental force of the universe. At the largest scales of talking about stars, galaxies, the universe, they're dominated by gravity. However, gravity does not get absorbed very well by matter. We're sitting here in a building, we're not floating off in space, we've got a building between us and the Earth. So gravity penetrates all matter. So for that reason, the gravity is passing through our detector, and it doesn't really dump any energy in the detector the way an electromagnetic telescope would pick up light. So we have to actually look at the ripples in space-time. We have to look at the effect of gravity over all of space.
And like other waves propagating through space, gravity waves too have various wavelengths or frequencies.
We need LISA because it's looking at a whole new part of the spectrum of gravitational waves. It's a whole new type of science we're doing. So with the LIGO detections, they're looking at objects that are roughly the size of the Sun, so anywhere from 1 to 100 times the mass of the Sun. and in their case it was about 30 solar mass black holes which were orbiting each other. Whereas with LISA, we're looking at galaxies merging. So it's no longer stellar-like objects, it's now galactic objects. So things which are maybe 1 million times the mass of the Sun, the big black hole at the centre of galaxies. When galaxies merge together, eventually these black holes collide. And when that happens, it rips a universe apart. And we're looking for that universe vibrating from these merge of these big, big events. Something you can never ever do that on the ground. So LIGO will never be able to see the events that we see with LISA.
The LISA mission will consist of 3 satellites precisely positioned to each other in an Earth-trailing orbit. There they will connect to each other via laser beams, forming a single detector.
So the big difference between LISA and LISA Pathfinder is the length of the arm. So in LISA Pathfinder, we had 2 gold platinum cubes in our spacecraft, and they were separated by about 40 centimetres. Whereas in LISA, the little cubes are separated by 2.5 million kilometres. So to put that in perspective, that's about 6 times the distance to the Moon. So it's a long, long way.
Work has begun on the LISA project. It will take over a decade to plan, design and build, then test the 3 spacecraft. When LISA launches in 2034, it will be able to detect gravitational waves from objects up to 100 times the mass of our Sun. The engineering challenges alone are daunting.
So the challenges of a mission like LISA or LISA Pathfinder is the fact that it's built with, I think we had 40 different companies from 14 different countries building aspects. And unlike some of the planetary missions or some of the also astronomy missions where you have a camera and a telescope, our whole satellite is one instrument. And if we go to LISA, all 3 satellites form one instrument. So everything has to come together, it has to work, and that's what happened. You know, we had a very great collaboration within Europe, and when it all came together, it worked as an instrument on day one.
None of that would have been possible without Albert Einstein, LIGO, and the LISA Pathfinder. Its success has paved the way for a whole new window into the mysteries of our universe.
Gravitational waves allow us to see the dark side of the universe, so the things which are not shining light, for example black holes. So now we can actually go out there and we can really observe these things which we've got no other way to see. And also, their gravitational waves were predicted by Einstein, and this is one of the main pillars of general relativity. And with LIGO, and even better with LISA, we can really start to probe general relativity and see that is actually theory which governs the gravity of the universe.
We have been observing our home for 40 years now. In the last 20 of those, we have focused intensely on planet Earth. With new technologies and capabilities, accumulating a massive data that is now revealing a complex and ever-changing living planet. They've been watching us from space for the last 2 decades in high-resolution detail, watching our every move. The clouds and aerosols, winds and hurricanes, forests and cities, droughts and floods, the ocean currents and plankton, life in the ocean and on land. Land cover, aerosols, chlorophyll concentrations, wave heights, ozone concentrations, atmospheric moisture, the human footprint, sea level change, and temperatures and moisture in the soil. Now scientists have a high-definition data set spanning 2 decades to study and to learn from.
Well, NASA has a fleet of satellites that are always measuring Earth. They're looking at land, oceans, atmospheres, ice all together. The particular visualization represents the measurement of all life on Earth over 20 years. I personally find it mesmerizing. You're watching the Earth breathe here. The seasons are changing, ice is coming in and retreating. You can see the forests on land in green, expanding and contracting. You can see the deserts moving to the ocean. You can see biological deserts in the centers of the ocean, represented by blues and purples. And then as you look farther north in the Atlantic or towards Antarctica, you can see these greens and yellows. Explosion of life in the ocean, just like on land in the spring and summer. Incredible.
What we see for the first time is how the oceans and the land behave at the same time through time for 20 years. We've never had data like these before. Half of our photosynthesis occurs in the oceans and the other half on land. And having these data to show both at the same time, day after day, month after month, year after year for 20 years, is a great tool to study life on Earth. NASA has observed many aspects of the coupled land-ocean atmosphere system and how they interact. For example, we see that with warmer surface temperatures, the growing season is getting longer at higher northern latitudes, and spring is coming earlier. With satellite data, we're able to map this continuously across the Earth's surface and across the United States and across Alaska. Before that time, you had to rely where you had weather stations, and so you had points here, points there, but you never had continuous data like these. So using these data, we can look over very large areas and see regional effects, and sometimes these effects are positive in that nothing bad has happened. So it's only with these data we're able to do this over all these areas at the same time. And this is made possible by the use of Earth-viewing satellites, which orbit the Earth day after day, month after month, year after year. And these data are the basis for saying these things about Earth with confidence because we measure them.
The view from space is opened our eyes to so many different things. You can see transitions from La Nina to El Nino, represented by huge blooms of life across the Pacific Ocean at the equator, bigger and wider than the United States. You can see greening of the Arctic. You can see earlier summers, later winters, and you can see the emergence of harmful nuisance algae.
Charting the carbon dioxide cycle through the atmosphere, land and ocean is essential to understanding the environmental changes that man is driving. Higher carbon dioxide, or CO2, in the Earth's atmosphere appears as red and yellow, while lower than average CO2 is shown as blue. The pulsing of the data is due to the day-night cycle of plant photosynthesis. As CO2 is lifted away from the surface, it is rapidly spread around the world by high-altitude winds. CO2 builds up in the northern hemisphere winter when plants are dormant. By summer, photosynthesis draws massive amounts of CO2 out of the atmosphere, resulting in lower CO2 throughout the northern hemisphere. The growth and decay of vegetation in the northern lands causes the seasonal change in atmospheric CO2. Long-term, however, it is human activity that is increasing overall CO2 levels.
So 2017 was the second warmest year ever recorded and the warmest non-El Nino year. That makes 5 of the warmest years ever recorded just since 2010. And NASA scientists have taken weather station data from over 6,000 stations, and we've connected the dots to understand how our Earth is changing. In this animation, you can see those warmer temperatures growing as we look at how much the high latitudes in places like Alaska have warmed since 1950. So across the globe, we're seeing a consistent trend towards warming, but with twice as much warming across the high latitudes like Alaska.
This rapid increase in overall global temperatures is clearly defined when satellite data is added to the model.
The ability to expand your senses into space, compress time, watch visualizations like these, see how the ecosystems of land, ocean, atmosphere, ice all interact, and then be able to rewind it and watch it again and again. It's amazing.
Ask any astronaut. When they look down at Earth, they see a single environment. No borders, no claims, just a single planet which we all have to rely on. With this data, scientists can check up on the health of the planet. One primary concern is the ozone layer.
So we know the Montreal Protocol was a huge success. This was signed in the late 1980s when scientists and policymakers from around the world gathered together to try to save the ozone layer.
The chemicals they regulated persist in the atmosphere for many decades. They thin the ozone layer and they create a seasonal hole over Antarctica. They basically take away part of our planet's natural sunscreen, and that increases the risk of skin cancer and damage to plants.
Scientists have projected the ozone hole will disappear almost completely by 2075, but several factors could delay that outcome.
There are some industrial compounds that are not banned by the Montreal Protocol, but as they enter the atmosphere, they will also hurt the ozone layer.
But the unregulated compounds have a short lifespan in the atmosphere, unlike the chlorofluorocarbons that were originally regulated. So they have a short-lived impact on ozone, and we don't think they'll delay recovery by more than a few years.
We projected by 2050, more than half of the ozone-depleting compounds in the atmosphere will come from long-lived substances banned by the protocol.
Because these compounds stay in the air for such a long time compared to the unregulated short-lived compounds, they will have a disproportionate and lingering impact on ozone. Any non-compliance with protocol can have significant consequences.
And the really big uncertainty in ozone layer recovery is climate change. There are many naturally produced ozone-depleting substances that are emitted by the oceans. And as the oceans continue to warm due to climate change, those emissions will increase, and that will further delay ozone recovery.
Scientists want to understand better how climate change will affect ozone recovery.
This is a hard problem. As a scientific community, we need to work on this major issue. We now have a powerful new tool to simulate atmosphere and its interaction with land and ocean to study this issue. And that's what we're going to do.
At the top of the world, however, the Arctic ice continues to shrink.
Sea ice is the ice that grows and melts within the Arctic Ocean. It grows in the wintertime when it gets cold and melts through the summertime. And so it doesn't raise sea level, but it's very important for the global climate system because the ice is very bright and reflective, reflects a lot of the sun's energy that comes in during the summertime and helps keep the Arctic cooler. It's like a refrigerator for the global climate system by keeping the globe cooler than it normally would be without sea ice. And as we lose the ice, it's like we're opening the refrigerator door and not cooling things as efficiently as we used to.
Constant observation since the 70s lets us see a trend.
The Arctic sea ice has been changing quite rapidly. We've seen a decline over 35 plus years of a record. The last 15 years particularly, it's been accelerating. So really, it's become a matter of when, not if, we lose the Arctic sea ice, because we have a lot of warmth in the Arctic. It's going to continue to warm. We're going to continue to melt sea ice. There's uncertainty as to exactly when that will happen, but sometime in the not too distant future, faster than we used to think, the Arctic Ocean will be substantially ice-free by the end of summer. Arctic sea ice is not the only place we're seeing big changes. We're also seeing big changes in Greenland, which is the big mass of ice on top of the continent, and we're seeing more and more melt. We're seeing ice calving off as icebergs, so we're seeing big masses of ice loss over the last several years. That means that that ice is going into the ocean, that's raising sea level, so that's going to have big impacts down the road as we continue to lose more and more ice from Greenland.
Ancient air bubbles trapped in ice enable us to step back in time and see what Earth's atmosphere and climate were like in the distant past. Today we stand on the threshold of a new geologic era which some term the Anthropocene, where the climate is very different to the one our ancestors knew.
We can see that a warmer world means that there's an impact for warming temperatures in the Arctic, melting sea ice. That sea ice leads to larger sea level rise. So NASA scientists are on the ground in airplanes and using our satellite data to understand how what starts in the Arctic doesn't actually stay in the Arctic.
The hope is that all this data collection will mean that real-world problems can be reassessed and new angles explored. A case in point, dolphin and whale stranding. Could this accumulated satellite data help address the problem? Cape Cod in the US state of Massachusetts is home to one of the most frequent marine mammal stranding sites in the world.
If we can get there quickly and provide supportive care, they have a much better prognosis in terms of survival.
Scientists know very little about why these mammals strand, and only a quick and efficient response in these events will save lives. Katie Moore works on the front line and has fine-tuned rescue efforts.
If we can develop an algorithm that pieces together the different variables that may be causing mass strandings or driving mass strandings, then we have the ability to then prevent them. We can have teams that are out on the shore looking for animals in those hot spots, knowing that all those variables have come together and this is the likely point in time where we're likely to see it. But we can also have teams ready to respond so that if they do strand, we're there that much faster and more animals will survive the event.
Marine biologists from the US Bureau of Ocean Energy Management were also looking at this problem.
For the large proportion of these strandings, the animals are across the ages, in pretty good health, and there's no really immediate evidence as to why they actually strand.
One possibility is geomagnetic perception, the ability to navigate using Earth's magnetic field, which is believed to be used by marine mammals. Could changes in the magnetic field confuse the animal? Geomagnetic pulses or storms can be caused by space weather.
Geomagnetic perception is one of the theories, and I thought, well, if a magnetometer can pick it up, maybe the animals actually can pick it up.
Dr. Reed consulted with NASA at the Goddard Space Flight Center.
The coolest thing was that we realized that nobody had really taken a cold, hard data science analysis look at the problems.
What we were trying to look at here was if there was a potential driver or relationship or correlation between the occurrence of mass strandings and any solar activity.
The data that we have correlated or analyzed so far is information about the local geomagnetic conditions. We have long data records from geophysical observatories of the local geomagnetic field variations and marine mammal stranding.
Their analysis was inconclusive. They needed more data from other environmental conditions.
Easy fixed correlation between a geomagnetic pulse and a stranding doesn't seem to be very evident, but what it does show is that there are multiple variables involved in this equation, and that the geomagnetic storms could just be one very small part of it. Significant still, but it looks like there are multiple oceanographic and environmental elements.
more data in hand, it was time to expand the team. They recruited statisticians and the expertise of NASA Earth Science data analyst and oceanographer Erdem Karakollu.
A data set, no matter its shape or content, always has a story to tell. Trying to figure out how different data are connected, I think, require a wide diversity of skills and background knowledge.
For example, I'll be explaining how a mass stranding occurs and how we respond to try and understand why I'm presenting the data in a certain way. And my colleagues from NASA will look at me and ask questions that I wouldn't think to ask because I take for granted my understanding, and they're coming at it from a totally new angle with no background.
These data sets may reveal a pattern, allowing scientists to predict the likelihood and location of mass stranding before it happens.
We've really just sort of slowly peeled the first layer of this onion back. And I think that there's so many more layers that still need to be addressed and looked at. And I hope that we can actually find additional collaborators, additional funding partners to really bring all the data that's really available to really give this the study and the scrutiny that it deserves.
And we are also going to make all these data sets available to the entire scientific community so that we can utilize the entire scientific community to take an attack and approach this problem.
I think that there will be other things to take and run with, get new ideas, maybe add more data. And I'm hoping also that it will be a model for how projects can then be open to the wider public.
The ability to release animals after they've stranded is tremendous. When we do that, I mean, that's the best feeling in the world after all of that hard work.
Those questions that seem unanswerable, if you give them time and support and effort and put people on them, we can do amazing things.
Data from satellites reveals the interconnection between air, sea, and land. This is a visualization of three aerosols: dust, smoke, and sea salt. The Calypso satellite data reveals in 3D how dust from the arid Sahara Desert is lifted by the winds each year and transported nearly 5,000 kilometers across the Atlantic Ocean. Some of it settles in the Amazon basin, the largest rainforest on the planet. Sahara dust contains phosphorus, an important nutrient for plants. Calypso shows that on average, 182 million tons of dust leaves Africa each year. When the Sahel was dry, the dust transport to the Amazon in the next year would increase. When it was wet, dust transport would decrease. We can now track global precipitation, wind currents, cloud cover, and ocean temperature. Satellites have detected a shift in phytoplankton populations across the planet's 5 great ocean basins, showing the expansion of biological deserts where little life thrives. Diatoms are one of the most abundant types of marine phytoplankton, but a new 15-year-long NASA study reveals global populations have declined. Diatoms, like all phytoplankton, have chlorophyll, the same photosynthesizing pigment as plants. They occupy the surface of the ocean, where they harvest light from the sun. In large numbers, diatoms form colorful swirling blooms that can be seen from space. According to the study, significant decreases in populations, shown here in red, are mainly in the northern hemisphere.
Diatoms rely on nutrients such as nitrate, silicate, and iron to reach the surface layer where they live. What our study shows is that the availability of these nutrients has changed due to the way they cycle within the water column.
Diatoms occupy the surface area of the ocean called the mixed layer. Nutrients collect on the ocean floor and are cycled up to this layer. Various physical forces can cause the depth of the mixed layer to become shallower, so that fewer nutrients reach the diatoms. Without these, their populations decline. This map shows areas on the globe where the depth of the mixed layer shallowed.
It's hard to pinpoint exactly why this change have happened. Things like wind, circulation, and temperature can affect the way these nutrients are brought to the surface layer. We hope a longer study can yield more information on whether these changes are in fact a trend or variability.
Next-generation satellites are reaching orbit now to continue this important work. They will collect data, maintain observation continuity, and allow scientists to track the changes in our environment. They can then model dynamic simulations to better understand this unique planet and the myriad of life forms that rely on it.